Okay. Can you see now? It's preparing it.
It should be on now. But your audio quality is really bad. I'm not sure why.
We got a couple of interruptions on Zoom so far, so sorry for the audience. Hopefully this will work out well now.
I'm guessing that worst case scenario, you can disable video and just do voice.
Okay, no problem. So I think the video stream is on now, so we're all good. Okay, so go back to the presentation now. Sharing my screen.
Maybe you should also try disabling your camera, because we can barely hear you.
Okay. Okay, is it now done?
It's slightly better, but not by much.
Okay. Not sure how to improve this. Is it better? Is it any better now?
Now it's better.
It's better. Okay, great. Please let me know if there is some interference, and I can maybe break for a second. All right. So this is the program. As I was saying, there are 3 parts. The first part by myself, I will introduce the design space exploration from a high-level perspective. Then Artur will give a demo on HyperMapper. This is a hands-on, so feel free to pull out your laptop and run the commands with Artur. The second part will be on the spatial programming language compiler by Matt. Spatial was introduced in 2018, not PLDI. So this tutorial is a follow-up on that, and we'll be focusing on the spatial feature of space exploration. After that, Matt, we will talk about, we will run a demo on the spatial HyperMapper. And the third part will be about design space exploration advanced topics by Artur. At the end, we will stick around for a little bit longer for questions, question answer session. And we will also stay a little bit longer for, just in case someone is running on install issues, we may try to solve them in real time. Today's objective is to be able to use a plug and play DSE tool. So the objective is to have so this is a tutorial, so feel free to interrupt us whenever you wish. You can ask questions by raising your hand or by asking questions directly on the Slack channel. So feel free to use the Slack channel, and we'll try to answer questions in real time. The HyperMapper tool that we will introduce today is open source and online. So you can find it on GitHub. It's called HyperMapper, and you will be also able to find all the material online on the wiki of the HyperMapper repo. So you can go to the quick start guide, which talks mainly about HyperMapper, and then on the spatial use case on the bottom for the spatial quick start guide. So without further ado, we are a few minutes late because of this technical issue that we had. But without further ado, if there are no questions, I will proceed to the first part of this tutorial. you see it all right? Can you guys see this presentation right? Seems that there is a bit of an issue in the presenter mode.
Now I
Can you
think
see
it looks
it right?
good.
Okay, great. Thanks, Artur. Okay, so let's talk about design space exploration. This is a high-level introduction. I'm Luigi Nardi. I'm an assistant professor at Lund University and a researcher at Stanford University. Please feel free again to ask questions. This is a tutorial. We would like to make it pretty interactive. So you can raise your hands on Zoom and ask questions also on the Slack channel. These are the main papers behind this set of talks. As you can see, we've been working on this topic since 2016, there are a bunch of references you can refer to in case you are interested after today's tutorial. The slides are available online already, so on the website. So feel free to download them if you from now. The spatial compiler was introduced 2000 at PLDI. We introduced spatial at that time, and this was the goal of spatial was to be a compiler for the design of CGRAs. Today's tutorial will be mainly about FPGAs. So the spatial compiler here on the left lowers user high-level programs into synthesizable chisel. So we go from the top here to the bottom through a series of compiler passes, and we will eventually, the compiler eventually synthesize chisel code. And so the high-level programming language will be introduced a little bit later by Matt. So this part will be a little bit generic on the compiler. The first pass in the compiler performs basic hardware optimizations and estimates a domain for each design parameter. This concept of design parameter will be very common in this 3-hour session. The idea here is that the user is asked by the programming language to define these high-level parameters that will affect how the code is generated and the performance of the final application on the FPGA. So these parameters are important for achieving high performance. We'll talk a little bit more about the parameters in the next slide, also more specifically. And Matt in his session will also very precisely talk about the parameters in the spatial code. The second part here computes in the compiler computes loop pipeline schedules and on-chip memory layouts for some given value for each of these design parameters. And this pass here estimates the amount of hardware resources and the runtime of the application. And here there is this pass that is called design tuning, which is optional, meaning that the user can define a design parameter set to run his application. At the same time, this design tuning phase here is an automated phase that will provide the best parameters for a given application. And the whole talk today is about this design space exploration phase here in the design tuning phase. After that, the compiler unrolls loops, retimes pipelines, and performs on-chip memory layout. The optimization here are computed based on the analysis of the previous phase, of course. And finally, the compiler generates chisel design, which can be synthesized and run on the target FPGA. So the idea of this tutorial is to replace the design tuning phase with an automated design space exploration tool called HyperMapper. And HyperMapper is one of the main software we will introduce today in this session. So as you can see here, this arrow that goes up, it's a feedback loop where the HyperMapper design space exploration tool will run a bunch of different iterations and will eventually provide the best found parameters for that specific application. So this the compiler parameters are specific to each new application. So when we talk about design space exploration, we usually define a search space, and these are also, like, we can call them optimization knobs. These design parameters are automatically provided by the spatial compiler, and they are in the form of a tile size, inner and outer loop pipelining, metapipe, unrolling factors, and memory banking and parallelism. So these input parameters are all about defining what's the behavior of the memory hierarchy and the parallelism in the code. So it's about parameters that will give a direct impact on the performance of the application. At the same time, we also have output parameters, which are the objectives of the optimization. And they can be in the form of minimizing clock cycles, for example, minimizing runtime, maybe objective one. And then other objectives can be, for example, minimizing the FPGA logic utilization. Like, for example, on an FPGA, we have a limited amount of logic, and we would like to reduce the amount of logic that we use. This may be an objective. And this may be useful for fitting multiple applications on the same FPGA, for example, or as a proxy for energy consumption. Of course, energy consumption can be itself a metric for optimization. Accuracy of the code, for example, can also be considered an optimization metric, and so on. Another output is the feasibility constraint, which basically is a signal that the compiler provides on the fact that the design fits the FPGA or not, for example. So this is just an example, but in the context of spatial and FPGA design, usually the parameters that a user chooses can not fit in the FPGA. So this has to be considered in the design space exploration. Otherwise, we will just come up with unfeasible design points. So this is a little bit like the way it looks like in spatial. So here, a bunch of applications on the left. And the ones on the top are pretty small applications with only a few parameters. And then we go on the real world applications on the bottom, from GDA to MD grid, or shallow convolutional neural networks and so on, where we have a bit more parameters. And if you look at the search space, this is a search space that is pretty big. So it's not really possible to explore a space with trillions of combinations by hand. If you look a bit at the motivation of this work, and we plot the runtime response surface of a benchmark in SlamBench, which is a benchmark suite. Here I'm showing parameter 1, parameter 2. It's not really important what the parameters are in this specific context. And if we show the response surface, we can notice that the response surface is nonlinear, multimodal, and non-smooth. So this makes the optimization tricky, meaning that it's difficult for a user optimizing this kernel here, this application here, to find the minimum in this landscape. So that's why we believe that a data-driven approach may help to get better results, and we'll show some evidence of this. So to define this design space exploration from a high-level perspective, we've been talking about the input space, or the search space, or design space here on the left. Here I'm defining 3 parameters. The first one, P1, is a real parameter. So usually real parameters are defined with an interval. So here it's between 1.5 and 6.3 for the sake of the example. Parameter 2, which is an ordinal, as I was mentioning before. These are numerical values that are also ordered. Here it's from 1 to 7, but potentially can have holds here in this ordinal type of variables. And parameter 3 is a categorical parameter. So categorical parameters are like true, false, for example, type of parameters, or you have multiple classes that fall in that category. On the right, we have an output space or objective space. Here, I'm defining an objective space that has 2 objectives. Of course, we can have from 1 to n objectives in general. And the function that we're trying to optimize, which often is a software that we're trying to optimize, maps the input into the output. So the red dots are mapped into the output, so giving the blue dots by this function f, which is a vector-valued function. So if we sample the input space, we end up in the output space on the blue dots. And if we are trying to minimize the function f, we'll try to focus on this side of the objective space. And if we are maximizing the function, we are trying to focus on the upper right corner of that space. And this is the feasibility region. So this is what I was mentioning before. In FPGAs, this will be the region that says this design on the left fits in the FPGA or not. Any questions so far? Okay. So by working on design space exploration for a few years, we noticed that there are a bunch of different features that come up over and over again. The first feature is this in the context of using a plug-and-play design space exploration tool without really having to understand the detail of the design space exploration tool to use it. So if we have a new compiler design or a domain-specific language, for example, that we would like to leverage the DSE capabilities in that new language and compiler, we need a bunch of different features. And we studied this problem and we realized that there are a bunch of features that are really important to be able to use this DSE tool out of the box, just in a plug-and-play fashion. So one of these features is the type of variables that you can encode in your problem. So here, these 4 variables are very important. So real, integer, ordinal, and categorical variables that I call REOC variables here. An example is tile size. So tile size is an ordinal. And parallelism, for example, do we parallelize the code or not, is a categorical variable. A second feature is the prior knowledge. Prior knowledge means that sometimes the user of the design space exploration tool has been optimizing by hand their software for a long time. So they would like to use this information they've been growing for years into the optimization process. So it's useful to be able to inject that information in the optimization to make the optimization more effective and efficient. So an example of this is the number of threads on a CPU with 4 cores. So let's suppose that the CPU is a multi-core CPU, and it's hyper-threaded, for example, with 8 logical cores, for example. Then in that case, you can pretty much guess that if you use only a thread, it's probably not going to be optimal. And if you use 8 threads, it also may not be optimal. So maybe you want to guess that the optimum value is between 4 and 8 with a peak around 6, for example. So we like to maybe use a Gaussian shaped around maybe 4 or 6 to say that you would like to inject the knowledge of I believe the user, the user believes that the optimum will be achieved, best performance will be achieved around 4 or maybe 6 cores. And non-feasibility constraints, as we mentioned before, are important. This is all about points in the design space that are not feasible and they're not known in advance. So you need to run the synthesis, for example, to understand if these points are actually feasible or not. And the last is the multi-objective optimization feature. Here, it's if you're trading off between runtime and area, if you're trading off between runtime and energy, and things like that. Hey, Matt, I think I've seen a question there. Is there anyone that wants, is there a question pending?
There was a raised hand, but I think the person raised their hands. Maybe they want to ask the question.
I just unmuted someone who asked the question.
Okay.
Looks like Shadi.
Thanks. It's a bit difficult when I'm in presenter mode here to see what's happening, so I'm a little bit blind. But if there are questions, please raise your hands, and Matt and Artur will enable you to ask verbal questions.
So it looks like Shadi has a question. I'll give a few moments to talk.
Okay, maybe never mind. Shadi, you can ask a question later on if you want. So if we look at the tools that can be used today for as a plug-and-play tool for design space exploration, I'm pretty sure that this is not an exhaustive list, but this is a list of tools that can be potentially used for design space exploration today. And if we list the 4 features that we showed in the previous slide, we call multi-objective. REOC is real, integer, ordinal, and categorical variables. Constraint is for feasibility constraints, and prior is prior knowledge. So here you can see that a bunch of these tools don't really have the potential of being used in a plug-and-play fashion. And they're all missing different features, which make it not really possible to just use them in a new tool chain, unless the tool chain needs less features. A very famous tuner, for example, is OpenTuner, and you can see that in OpenTuner there are a bunch of things that cannot be done out of the box. The feasibility constraints, for example, it's one that is missing, and we believe that is a very important feature. The prior knowledge is also extremely important, and the multi-objective is also kind of lagging behind in OpenTuner. You can scalarize the objectives, but it's not really a general approach to multi-objective. So HyperMapper was designed with these 4 features in mind, and so we have all the ticks here on the checks on the 4 features, and we will introduce these features during this session today. So in general, from a high-level perspective, the design space exploration solutions are multiple. So the one that's very, very common is manual optimization. So you have an application and you want to you have a bunch of parameters that will affect the performance of this application, and the user, that's usually an expert user, will run manually a bunch of different experiments to optimize this application. So this obviously needs a human expert, and human experts are rare, but also it takes a lot of manual labor. And that doesn't seem to be a very optimal way of proceeding. Also, if you have many different applications that you want to optimize, and also if you want to have something that runs in the compiler. Some other approaches are automated, but architecture dependent. And so the fact that the approach is architecture dependent means that it doesn't generalize to other architectures, for example. So if once that you move to a different architecture, the whole method has to be redesigned with the new architecture in mind. So this is the non-generalization is a behavior that you would like to avoid. Another one is grid search, where you basically take your search space and you discretize it in a fairly coarse way so that you can actually run all the grid and collect the results and just select the best outcome from that grid search. Usually grid search is not really feasible most of the times because for the search spaces that I was showing before, those are very big search spaces. So grid search will only capture a very limited amount of points in that space, which will lead obviously to worse performance results. Random search is a very common way of doing this, and it's actually random search has very strong theoretical guarantees that you will eventually find the true optimum if you run it for a very long time. The issue is that random search is very inefficient, so that's the reason why random search is not very appealing for design space exploration. A bunch of other tools are based on evolutionary algorithms, and evolutionary algorithms, I will argue, that also are high in sampling budget, meaning they're not very efficient in terms of budget, but they work well. So we will talk a little bit more about this in my next slide. And finally, Bayesian optimization, which is a sampling efficient method based on machine learning modeling. We argue that Bayesian optimization is a very important framework for design space exploration in the case where the budget of the sampling budget that the compiler has is small. So as a rule of thumb, I think we can have this idea in mind. So if we're going, so what type of algorithm to choose for the design space exploration? In HyperMapper, we have a bunch of different optimizers that are already implemented and ready to use. The idea is that if the sampling budget is small, meaning here on the left side of this picture, we usually recommend to use model-based algorithm, where model-based means that some sort of model, surrogate model is developed on the fly based on the data that is collected over time. And then the model can be used to optimize that function. But if the budget is bigger, then in that case, direct algorithms are usually more effective because they need less computing in the optimizer, and they can, since the budget is big, you can explore much more. So they usually fit well in that setting here. So in HyperMapper, we have direct algorithms and model-based algorithms. The direct algorithms that we have are random sampling, multi-start local search, and evolutionary algorithms. And the model-based algorithms are all based on Bayesian optimization. So we have different versions of Bayesian optimization algorithms, but they fall all in the same umbrella of Bayesian optimization. So this is the high-level view of what's inside the HyperMapper box. In practice, a user will pretty much need to understand this scheme on which algorithm to choose, and we will see that later with the demo. From a slightly more formal perspective, the design space exploration mono-objective formulation can be formulated this way. And so this is the only kind of technical slide that we have in this presentation, but some may benefit from a little bit more of formalism. So here we're finding a global minimizer of an unknown objective function fx. So again, the objective function fx can be a software, a compiler, hardware design process, and so on. And we have a set of q unknown feasibility constraint functions, ci of x. And we can write this problem as the argmin with respect to x of fx. So here we want to find the x that minimizes the function f. We're not just interested in finding the minimum of fx, we're interested in finding the x that minimizes fx. So x are the parameters that we discussed before, and f is, in the spatial case, is the spatial compiler and the design point that it will provide to the FPGA. So we're subject to a certain number of constraints, C of ix, that have to be less or equal to a certain number pi. In addition to that, usually for design space exploration, the objective function fx and the constraints ci of x have no simple closed form. So think, for example, to a software. There is no closed form for a software, or at least it may be very difficult to obtain. And they can be evaluated at any point x, but evaluation is expensive. So every time we evaluate f of x with a giving an x, the evaluation is usually expensive. Think, for example, the synthesization of a program that may take a long time. And gradients are usually not available, meaning that they're either available at prohibitive cost or they're not available. Think, for example, when you have categorical variables. In that case, gradients are not easily computable. Here I'd like to show an illustration of what Bayesian optimization looks like from a high-level perspective. And this is also related to the surrogate model, the model-based approach to design space exploration. So in this case, we are using Gaussian process, which it's not really important to understand very well what it is. But here, the Gaussian process is this surrogate model that provides us with mean and variance. And I will explain a little bit more what I mean by that. So here we have a design space that is the x on the x-axis, that is defined between -5 and 5. And then we have the function that we want to optimize on the y-axis, the fx. The function that we want to optimize is in blue. That's the true objective. And we don't know what that looks like. So for the sake of this example, I have it in blue. And we would like to find the minimum of this function that is situated around -3 on the x-axis. The red point is a sample of that function, meaning that we gave, at the beginning, we gave this x equal 2, roughly speaking, and we evaluated the fx, so we know what fx looks like around there. So the red point represents the fact that we have knowledge about the value of fx at that point. We can fit a probabilistic
Luigi,
model. Yes.
Luigi, sorry. We have a question in chat. Maybe you want to take that and answer. Augustine, do you want to ask the question verbally? If not, Augustine wants to know what do you mean by the function f is not known? Isn't it the case that f is known but very expensive?
Right, excellent question. So this is this was the previous slide, I think, here. So we're saying that the function f is not known in the sense that so the function f is represented by a software, right? And so it's a complex program, can be millions of lines of code, and the function f is represented by this code, and we want to optimize this code. So in some sense, it's known because we have the code, but we don't have a closed form for that function. What we can do is to evaluate that function f of x by giving a value x. So if you give me an x, I can run the software and collect the value fx. But a priori, I don't know exactly what f of x looks like. Is this answer clear, Augustine?
Yes, thank you. That's perfect.
Yeah. Thanks for asking questions. So please feel free to interrupt whenever. It's a bit difficult to, we are in a virtual setting, so it's a bit difficult to see what's happening in the audience. So an interaction with the audience, it's highly recommended for the tutorial. So feel free to ask as many questions as you want.
Sorry,
okay?
Can I ask a follow-up question?
Yes, of course. Right.
Yes, sir. Maybe you mentioned it and I didn't understand. So now I understand what F being unknown means, but what about the constraints? You also say that they are not.
Yes. Yes.
unknown.
So it's a bit on the same thing. So think, for example, to the FPGA design that the example that we mentioned before. So to understand if the constraint is like, does this thing fit in the FPGA or not? And to do that, you may need to go through the evaluation of the design point first to understand if you actually also fit in the FPGA, not only to understand what's the performance of the FPGA. So the performance will be the f of x, right? So you have a design point, which is the x. You run it through the compiler, and you will potentially synthesize it to the FPGA. Then you run the FPGA on that application, right? And you collect the performance of that application, which is the f of x. But the compiler can also prevent you from doing that and saying, this application doesn't fit in the FPGA. That means that this design, the design that you chose, the X, doesn't fit in the FPGA. So the compiler will get back to you and tell you, this design is unfeasible. So that's why they say it's unknown, in the sense that you will know when you evaluate it, but you don't know it in advance.
Thank you. The example made it very clear. Thank you.
Okay, great. Okay, so let's go back to the Bayesian optimization illustration here. So I explained what X is and what Fx is here. And the blue function is the true objective. And the GP model is a surrogate model that gives us this error bars in gray. And by sampling the function means that we evaluated f of x, and we know that the value is in the red dot. And so at this point, Bayesian optimization will evaluate this surrogate model, and we'll see, for example, here on the left, there's the mean and variance are very, so the mean of this is low and the variance is high. So it decides to sample from there. And then again, on the right side, so looking at the variance and the mean, since we're minimizing this blue function that we don't know in advance. So we work on the variance and the mean of this surrogate model. And so we'll eventually explore the space in an intelligent way to get close to the minimum as fast as possible. As you can see now, it doesn't really make sense to sample on the right side anymore. And so the Bayesian optimizer focuses on the left side until we hit the optimum. So we call this process Bayesian optimization, and this, I think, is one of the main contributions in the HyperMapper tool. This works out of the box in the design space exploration setting. So this is a bit high level. I invite you to look at the papers if you want to know more about what's happening inside the box. So the high level view of HyperMapper
Luigi?
is that, yes.
We have another question. Raika, do you wish to speak the question with voice, or should I read it for you?
Sure. Sorry, I didn't get what exactly FP or FPGA is. What does it stand for?
Oh, right. FPGA is a field programmable gate arrays. FPGA is a chip that is reconfigurable, meaning that instead of running on a fixed chip, the gates in the chip can be reconfigured from a software perspective. So you basically write a high-level representation of your application, and then the compiler will map the application on the hardware by rewiring basically the chip.
Got you. Okay, thank you.
You're welcome. So from a high-level perspective, HyperMapper has this three parts. So on the left, the user defines the search space. That is pretty much what I was showing before in terms of like the multiple parameters that won't need to be optimized. There is a first initialization phase, then calling here random sampling. So basically sample a random for a little bit, so just for a few samples, the search space. And then we can use that, that knowledge of what the function effects looks like to build a surrogate model. So this is the probabilistic model I was showing before. And this is a simple supervised learning approach where we have the samples that have been drawn random before. And after that, we use the probabilistic model, we optimize it, and we evaluate, we decide what to explore or exploit next. So the whole point on this loop is to very efficiently optimize based on what we've seen before. So this is a data-driven approach where we collect data over time, and we and so the Bayesian optimizer does the suggestion of what's the next point to explore in a very efficient manner. And on the right side, we obtain the optimum, well, the optimum, or the approximation of the optimum, I should say, which is also sometimes called incumbent. I will show some quick results. I think we're a little bit late with the schedule because of the technical issues that we had, but just have very briefly some results on the spatial real-world applications. So here we have a shallow convolutional neural network, a deep convolutional neural network, and a molecular dynamics grid, MD grid. And I'm showing the results for random sampling, the HyperMapper in red, random sampling is in green. The expert configuration, which is Matt, that is also organizing this this tutorial, has been optimizing this by hand. This is in black. And as we can see here, the automated optimization approach is faster than the expert. For example, on the shallow, we have a 2.74x speed up. Here, we are optimizing with respect to the cycles. So this is a mono-objective optimization problem, and we are optimizing with respect to the cycles with the feasibility constraint that is also taken into account by HyperMapper. On the MD grid, for example, we have even bigger result outcome. So this is a 10.4x faster than expert. And in the case of comparing HyperMapper with the random sampling approach, HyperMapper is 33 times faster than random sampling. And as you can see on the shallow CNN, for example, the optimization with HyperMapper happens in a very few evaluations. So you need to evaluate the f of x only maybe 10 times, maybe 11 or 12 times maximum to already get pretty much to the optimum. And that's also the case for deep CNN, and it takes a little bit longer for MD grid. So in summary, we introduced the problem of design space exploration from a high-level perspective in this presentation, and we will go more into the details in the follow-up demo and presentations. So next, we will see the spatial DSE and the multi-objective priors, constraint optimization features in HyperMapper. So this is a general solution to DSE. It's widely applicable at PLDI in terms of like PLDI applications in computer systems in general. This is interdisciplinary research I was mentioning before, and HyperMapper is the name of this umbrella framework that contains several optimizers that can be used out of the box. Here we're talking about Bayesian optimization, random sampling, and heuristics like evolutionary algorithms, for example. We also shown some real-world application spatial, and we will go more through that with Matt. So these are a bit of like info on HyperMapper. You can join the HyperMapper Slack channel. This is a different channel from the one that is being used from for the PLDI. This is a permanent channel that can be used also after the PLDI conference is over. The repo is there, and the wiki is pretty convenient to navigate all different features and options. There are a bunch of adopters of HyperMapper. And the objective today maybe is to expand a little bit this list and see if there is interest in other communities. So this is all I have for now. Are there any questions? Okay, so if there are no questions, I would ask Artur to go through the second presentation, which is a hands-on on HyperMapper.
Okay. Hello, everyone. Let me share my screen with you. Okay. Hello, everyone. Thank you, Luigi. As Luigi said, I'll do a quick demo now, a quick tutorial on how to get started on HyperMapper, installing HyperMapper, setting it up, and running it on a few simple examples just to see how it works. To start this tutorial, let's first install and get HyperMapper set up. Here, we use Python 3 to implement HyperMapper, and so we recommend using the Anaconda distribution of Python 3 to run HyperMapper. For this demo, I'm going to run install HyperMapper here in a new machine and run this tutorial with you. So if at any point you have any questions, let me know.
So
I'm
Artur,
running.
This is in the install HyperMapper on the right side, right? This page.
Can you see both screens, the install HyperMapper and the terminal?
Yes, we can.
Okay. Yes. This.
Artur, so this page here is the wiki at install HyperMapper, right?
Yes, exactly. This page is in the HyperMapper GitHub repo. If you go to the repo wiki and this install HyperMapper tab on the right, you will get this step-by-step guide to install HyperMapper, and I'll follow it briefly with you. So we recommend using the latest version of Anaconda to run HyperMapper. Here, I'm going to do this on a Linux machine, but you can also do this on Mac OS. And the installation is simple. You download the file, the installer from Anaconda. In this case, I have already downloaded the file. And then you run the installer with the bash command. Anaconda will ask that you read and agree to the license agreement. Which I'll agree here, and choose somewhere to install a location to install Anaconda. Here, I'll set it as default. I think someone raised their hands.
Yes, no problem. I'm answering those. Keep going, please.
Okay. So while Anaconda installs, we also recommend, if you already have Anaconda installed, we recommend that you create a new environment to run HyperMapper on, so that you don't have any conflicts with other tools that you might be using, and HyperMapper doesn't cause any issues on your setup. For that, we also provide here in the installation tutorial the steps that you can do to create a new environment with Conda. For this, we recommend using Python 3.7, but other distributions of Python will likely work as well, as long as it's Python 3. While we wait for Anaconda to install, which should take about 4 to 5 minutes, let me walk you through real quickly through the HyperMapper repo and the wiki page that we're seeing now. So as I said, and thanks Luigi for bringing that up, this wiki is on the HyperMapper repo in the GitHub, which is available to the public. You can access the wiki through this link right here. And in this page, we have several resources to help you understand and get started with HyperMapper. So we have a quick start guide that you can follow and understand the basics of HyperMapper. We have some pages to explain some features and components of HyperMapper, most of which we will go through this tutorial and the next sections as well. We have also some examples in the repo that you can follow and use to understand some of HyperMapper's features. And some of these examples we will use in these tutorials to show how these things work. In case you want to try them again at home later, you can follow these links in the wiki. And we also have links for some use cases, like a spatial use case that we're going to do in this tutorial, and some other advanced modes of HyperMapper, which we'll also cover here later. Also, while this installs, let me start with some briefing of the demo that we're going to do right now. The demo is in the HyperMapper repo. We're going to clone this and download it in a moment. You can find it in the example scenarios demo in HyperMapper. This is a Jupyter notebook that we're going to use. If you're not familiar, this comes with Anaconda and will allow us to run these cells of Python on the fly and see the results. So it's great for visualization. And before we get started, I would like to briefly introduce to you the function that we are using in these tutorials. Here, we are going to optimize this function that's called the Browning function. This is a classic function in the Bayesian optimization literature. It's very often used as a common benchmark to test and validate Bayesian optimization and in general optimizers. This function has two input parameters that we're going to be optimizing, x1 and x2 for simplicity. These parameters are real, defined between -5 and 10 for x1, and 0 and 15 for x2. This function also has three global minima that we are trying to find. The function at this minima is 0.39, and these minima are located approximately at -pi and 12, pi and 2.275, and 9.4 and 2.47. Also, for our demo, we're going to use, in some cases, a simplified version of this branding function where we give a fixed value for x2 and optimize for x1 only. This will give us some simplicity in the first experiment so that we can cover the basics of HyperMapper. Coming back to the installation now, here on the wiki, Anaconda will be done installing soon. These are the last steps that it does before finishing installation. And besides Anaconda, we will also have to install an additional package that doesn't come built in with Anaconda. I will follow these steps with you in a minute. And we will also clone the GitHub, the HyperMapper GitHub repository, which is the only critical step that you have to follow to install HyperMapper. And we'll also define a HyperMapper home environmental variable that it's not mandatory for HyperMapper, but this is useful for HyperMapper in many situations where we want to call HyperMapper and use it from a separate directory and not HyperMapper's root directory. This environmental variable is important to set up for the spatial tutorial that we're doing later. So if you're following with us and running these tutorials on your machine as well, we recommend setting up this environmental variable when we install HyperMapper. We should be done in a few seconds. Do you have any questions that we want to ask at this point, or can we move on?
Maybe we can pause for a little minute because I see that there are a bunch of technical questions that are happening right now. So I guess there is a lot to run here to get it. So there's a little bit of...
Yeah, there's a few hands raised, so I'll call on these people.
Can you unmute them so they can speak?
Yes. I think there are 3 people that are muted right now. No, Emmanuel, Lima.
Yeah, you guys can hear me?
Yes.
Yes.
Right. So I don't really like using Conda, so I ask, what exactly are the dependencies so I can install them with pip?
I see.
I think that Matt answered this question in the chat. Did you see it?
No, I don't see the answer.
Okay, it's in the chat. I will. Oh, I see. Because Matt, you sent it to the panelists, and I think we have to add that. I will copy paste it. No
Okay,
problem.
thank you.
Thank you.
I will answer there so that you have it in the chat.
Thanks.
Did you receive it now?
Yeah, yeah.
Great. Okay, so maybe Raika,
Yes.
please. Did you have a question?
No.
Okay, so for some reason your hand is still up.
Sorry.
Okay, no problem. No problem.
No problem. No problem.
Hampus?
Yeah, I had the same question before. I don't really like Conde as well. It seems to ruin my other Python stuff. So I just wanted the same thing. So I've already have my answer. Thank you.
Okay, great.
Okay, thank you.
Thanks. So please go ahead, Artur.
Okay, so moving on, just to finalize Anaconda installation, you were offered to initialize Conda at the end, and I recommend that you do to simplify our running here. And now Conda is done installing, so we just have to reload our terminal so that the installation starts working. Great. Now that Conda is installed, we have an additional package that we have to install, just a single package that does not come with Conda, which is called GPY. We can install it with a single line that's written on the wiki in case you want to copy paste. Otherwise, it's Conda install Conda forge GPY. This installation is quick, and if you're using pip, the command will be similar, just pip install GPY, and it should work out of the box. Just confirm that the package
can I ask please that the attendees that raise their hands before they lower their hands, because I'm not sure if they want to ask another question or. Thanks.
Thank you, everyone. Okay, so we installed GPY, and this is all that you have to install before start running HyperMapper. So now I'll clone the HyperMapper repo. Which will also take a couple of seconds. Then we can enter the HyperMapper repo, set the HyperMapper environmental variable, which we recommend doing. And then we can start running our demo. You can start it with the command Jupyter Notebook. In most cases, this will open a browser window with the Jupyter Notebook for you. If, like me, you're running on a machine without a graphical interface, you can just, like a virtual machine like I'm doing, you can just copy the link that Jupyter is going to provide and paste it in your browser. And you'll see that the notebook will open. Now, to navigate to the notebook, you can go to the example scenarios directory, demo, and then demo Jupyter Notebook 2020 Jupyter. Okay. Before we begin, are there any quick questions that we want to take from the installation? Okay. So, as I said, we'll be doing a set of examples here to show the basic functionalities of HyperMapper, and we'll do that with a branding function. Let's begin with a one-dimensional branding function where we're optimizing a single parameter, x1, which is defined between -5 and 10. To run HyperMapper, we'd have to define two components. First, we have to define a Python method for HyperMapper that HyperMapper can call with a parameter value and have it evaluate the value of the function at that parameter point. This is what HyperMapper will use to assess the performance of the parameters. Second, we have to define a configuration file that will tell HyperMapper the details of our optimization problem. So first, we define a method for our 1D branding function. Here, we define a method called branding function 1D. This method has to receive a dictionary as an input. This is the interface that HyperMapper will use. And this dictionary has a single key in our case, which is the input parameter that we are optimizing, x1. Inside this method, we will compute the branding function. Here, this is a simple syntactic computation, but we don't limit how complex this can be in HyperMapper. You could have any complex situation, any complex computation inside this method, call other methods, millions of lines of codes. You're free to define your problem. After we do that, after we have the computations done, all we have to do is return a number or a float to HyperMapper that tells us the performance of the algorithm for that parameter, so the metric that we're trying to optimize. We define the branding function running this cell. And with the following cell, we can see a little visualization of how this function looks like, a little visualization of the 1D branding. Here, we see the 1D branding with a blue line. As I said, the function is defined between 10 and -5, around here. And in this case, we have a single global minima that we want to define, the single global optimum here at x1 equal to pi. And we also have a local minimum here at around 9. This is the function that we want to optimize. Now that we have defined our method that allows HyperMapper to evaluate the parameters, we will then define a JSON scenario file which tells HyperMapper the details of the optimization that we're going to perform. So here I'm showing the fields that we specify for this JSON file. In the case of the 1D branding, we have a name for our application. Here we'll just call it 1D branding. We have the objectives that we want to optimize for our function, which we'll call simply value in this example. We tell HyperMapper how many random samples we want to do for initialization before running Bayesian optimization. So here we will do 3 random samples for initialization. And how many iterations, how many Bayesian optimization iterations we want to run, which is the budget for our problem. Here we will do 10 Bayesian optimization iterations. We will use a Gaussian process model, just like Luigi briefly mentioned in his presentation. And at last, we have a single input parameter in our case, which is x1, a real parameter defined between -5 and 10. We'll create this JSON here on the fly using Python, defining a dictionary with the fields that we've just gone through, and saving it, dumping it to a JSON file called example1D branding scenario.json. We can read this file back to have a sanity check and see that it looks like we want it to do too here, just to double check that's correct. Now, if you are with me to this point, if not, feel free to ask any questions and we can pause. If not, let's run, we're ready to run HyperMapper in the 1D branding function. And this can be done by simply calling this HyperMapper optimize method, giving it the JSON scenario file, and the branding method, the method that we define that HyperMapper is going to call. If we run this cell, HyperMapper will start the optimization process. First, it will start with the initialization, the random samples for initialization. Here we are doing 3 random samples, and HyperMapper will tell you which samples which are these samples. Here we have the value of the parameter that HyperMapper sampled, the value of the brane at this point, and a timestamp of this execution. This timestamp is computed internally by HyperMapper, and it's used to help HyperMapper order the order of points that it evaluated. In this case, since all of these points were randomly sampled at the same time, they all have the same timestamp. Afterwards, HyperMapper will keep printing for every iteration the parameter value that it tried and the value of the function at this point. The result of this exploration will be a CSV file, which will be saved on a CSV file, which we can open here to take a quick look if we want. And we see that it follows the same format where HyperMapper prints the value of the function, the parameter that it evaluated, the value of the parameter, and the timestamp that it used internally. Next, we can read this file back and plot it on a scatter and do a scatter plot to see the exploration that HyperMapper performed. And here we see the HyperMapper, the 1D branding function on the blue line, the initialization with red crosses, and the Bayesian optimization samples in blue and green crosses, with green crosses showing the later iterations. Here we see that HyperMapper started by finding the local minimum and exploring it. It moved in this region until it found the local minimum. And if we want to make a test later, we can leave this running for longer, and we'll see that HyperMapper will then start exploring again, as Luigi said, balancing, exploring the space and looking at this minimum region, and eventually converge to the global minimum here. You'll see similar results in your machines if you're running the tutorial with me. And in general, HyperMapper will always find one of the minima, usually the global minimum here. Now, let's do a second example. Here, let's change our problem a bit and optimize for the 1D branding function again, but this time with an ordinal parameter. Here, a quick recap. An ordinal parameter is a discrete parameter that's numerical and is ordered. What we have to do to run this example is to first define our new scenario file, telling HyperMapper that our parameter is now an ordinal. So if we go back, if we write the scenario file and read it back, we'll see that we have similar fields. We have a name, an optimization objective, an initialization phase where we'll do this time only 2 random samples, and the optimization iterations where we'll do 8 Bayesian optimization iterations. We'll use a Gaussian process model, and this time we have an input parameter x1, which is an ordinal and can take any of these discrete values that we specify. Since we have already defined our branding function in 1 dimension, we can already run this HyperMapper with the scenario file, with the JSON file. This will be the same, the HyperMapper will print the same feedback as before, this time much faster because we have a simpler space. And we'll again save the results on a CSV file, just like when we use a real variable. And we can again visualize these results here on a scatter plot. Here we show on black dots the possible values for the parameters of to the 1D branding, the parameter values that we defined, and we show again with red and blue and green crosses the points that HyperMapper explored. And we see that in this case, HyperMapper found the global minimum at the middle, started exploring again, and found the local minimum on the right as well. If you run this on your machine again, you'll find similar results. at last, let's show an example with the full branding function where we optimize for both parameters x1 and x2. Here, since we're doing a different function, we will redefine our branding function. So we define our function again. This time, we receive a dictionary which will have 2 keys with both of our parameters. We compute the branding function internally and return the value of the function. We'll also define our JSON file. Again, we use Python to define it here, and we can read it back to see the fields that we have defined. And here, again, we have the same fields. This time, we are doing 20 Bayesian optimization iterations, and we have 2 input parameters, x1 and x2. Both of them are real. x1 is defined between -5 and 10, and x2 is defined between 0 and 15. Here you might notice that I did not define the number of initialization samples that HyperMapper will do. We have in the JSON file a default for this parameter. So if we don't define this, HyperMapper will do 10 samples for initialization by default. If we run the branding function with this scenario file that we just defined and the method that we defined, we'll see HyperMapper again printing the output that we're familiar with by now. We have 10 initialization samples this time. For each sample, HyperMapper will print the values of x1 and x2, both input parameters. You can see them here. And the value of the branding function at that point, as well as a timestamp, which again will be the same for all of the random samples, all of the samples from the initialization phase, because for HyperMapper, all of these samples happen simultaneously. And then HyperMapper will do each of the optimization iterations. In this case, we requested 20 optimization iterations, and you print the value for both parameters, the objective function, and a timestamp. This should take a few seconds to run, and once it's done, we can once again HyperMapper will once again save the results to an output CSV file, and we can read this file and use the data to plot how this exploration looks like. Here we have 2 input parameters, so we show them in both axes. We use a heat map to show the value of the branding function over the space, with bright red points showing higher value function values and brighter white points showing lower function values. And here we have the 3 global minima of the branding with black crosses. And we can see that HyperMapper explored the space to understand how the function behaves, and then converge to this minimum at the bottom middle part. If you're running this on your machine, you might notice that HyperMapper, depending on how the initialization goes, will find different minima or even find multiple minima. If we give a bigger budget, HyperMapper will always find the minimum, start exploring, and start converging to other minimas as well, in case you want to try. We'll stop this tutorial here. I hope that this gave you a general idea of how to set HyperMapper to run on the problem that you have in mind or a new application. We have some advanced features that we'll cover in next sections of this tutorial. But now I'm going to give the word back to Luigi to move on to the next section.
Thanks very much, Artur. This was a great introduction to HyperMapper. We are slightly late with the schedule because of the technical issues that we had before. Here's the program. We're taking a little break right now, 5 minutes. I encourage people that have questions. I've seen that there are a bunch of install questions that are being asked right now. So we will meet again in 7 minutes more precisely, so 9:30. And we will be online answering questions if there is still some question pending from the previous 2 talks. So see you here in about 6 minutes now. Thanks. Okay, let's get back. It's 9:30. I think there is a raised hand first. Maybe Joel, do you want to ask a question? The raised hand is gone. Okay, so that means that we can start with our next presentation. At this point, we will go through Matt's presentation on spatial. Matt,
Okay,
are you
so
ready to go? Thanks.
Yeah. Yep, I just shared my screen, so hopefully everyone can see this. And hopefully everyone can hear me. Luigi or Artur, do you want to tell me if my volume's low, or can you hear me fine?
It's perfect. It's very good. Thanks.
Excellent.
Okay, cool. Give me 1 second. Okay. So this is going to be a pretty short talk about the spatial language and compiler. As Luigi mentioned, this was published in PLDI 2018. So if you want more details, you could refer back to that. The goal of this presentation is to just give you enough information so that you understand what spatial is, how it exposes a design space that HyperMapper can explore, and what you can do with spatial. So this is a language that's already integrated with HyperMapper. So if you want to test it out, you can go jump into spatial and do it. Hopefully, though, when you're watching this, you have your own task in mind and you want to integrate HyperMapper with whatever language or project you have. And hopefully this gives you the framework you need to do that. Okay, so brief introduction to spatial. We have to look at kind of the transition from instruction-based architectures to custom hardware that's been taking place over the past 20 or 30 so years. So what that means is if we look at what's happened with transistor scaling over the past 50 years, you can see that transistors have been getting smaller and smaller, so we could fit more on a given unit area on silicon. But the problem is recently there's kind of been a plateau of performance. So this plateau is one of the big reasons is the power wall. So even though we could put more transistors on the silicon, we're running into limitations with power delivery and heat dissipation. And the main problem is with these instruction-based architectures like CPUs, there is the instruction overhead. So even though you want to do something like, for example, an addition, a lot of the energy is going into other stuff like the the instruction pipeline and all that. So if we look at at a glance, the spectrum of compute devices that you have today, on the left side, we have CPUs, which are the least efficient for these instruction overhead reasons that I just mentioned. Beside that, there are GPUs, which are going to give you better performance by exposing parallelism and running things in parallel. Beside that, you can have more specialized devices like programmable DSPs. Beside that, and there's a bunch of things in the spectrum, but these are kind of the highlights. There's programmable logic. So for example, FPGAs, where you will design some circuit and put it into some chip that can run that circuit. And then finally, the most efficient thing you can do is make an ASIC, which is going to strip away all of your instruction, assuming this is how you designed your circuit, and do just the computation that you need to do. So the specialization is the key to achieving good performance. You want to cut out as much overhead as you possibly can to get the most out of the transistors that you actually put on your silicon. If we look at this in terms of programmability, the CPUs are the easiest thing to program. We've had 50 or so years of experience designing languages that target them. The ASICs on the right side are actually not programmable, but if we take one step to the left, we have FPGAs, which are programmable, but they're actually very, very difficult to program. We'll talk about that more in a second. And then if you look at this in terms of cost, CPUs are pretty inexpensive, and your ASICs are going to cost you lots of money to design, fabricate, verify, and all that. So as I mentioned before, this talk is about spatial, which is a language that kind of targets this slice of the spectrum here. Spatial will target FPGAs, and it also targets something called plasticine, which is a reconfigurable architecture that our research group has also developed. But for the sake of this presentation, we're going to look at just FPGAs. So quick introduction to FPGAs. Someone asked about FPGAs before. This is not at all a complete guide to FPGAs, but what you need to know about them are that they are field programmable gate arrays. So they're reconfigurable logic devices. What that means is you can design some digital circuit and then flash this onto the FPGA and actually run it in without having to design an entire ASIC to do this for you. So there's some on-chip memory, typically tens of megabits. There's some on-chip logic, typically in the millions of lookup tables and flip-flops, and there are processing blocks the DSPs, which are going to run your compute-like multiplication. So as I mentioned before, let's look at what languages there are for programming FPGAs and what role spatial serves in this landscape. So if you want to program FPGAs, typically you would go to Verilog or VHDL. These are your hardware description languages that let you describe a circuit in computer language, and then that will turn into the bit stream that you put on your FPGA. So there's some newer and more user-friendly alternatives like Chisel, PyMTL, BlueSpec, things that will let you automate some of the more mundane tasks of hardware design. So these are things that you can do if you know exactly what you want your circuit to look like. You can jump to these. The problem is they don't give you that much abstraction. You're still literally writing the hardware circuit that you want to put on the chip. And for large complicated algorithms or people who are not experts in these low-level languages, it's difficult to use the FPGA. So if we take a step up in abstraction, there's a lot of domain-specific languages that will let you target either a compute domain like streaming type applications or a particular application domain like networking or machine learning. And these are languages that you see here. So Aetherling, if you want to learn more about that one, you could learn more on Thursday at PLDI. There's going to be a talk on that. And so there's a bunch of languages. And the main problem with these, for our purposes, is that they're going to limit you to a particular domain. So if we step up in abstraction again, there are high-level synthesis tools. So these are the tools that let you write arbitrary, or not arbitrary, but familiar C code and put that code onto an FPGA. So they use pragmas to kind of fill in the gaps for the information that is not captured in software. These are languages like OpenCL, HLS, SDXL. There's also JVM-based approaches. So this is things like Lime and Spatial. And Spatial is what we're going to talk about a lot in this talk. So taking a step back and looking at hardware design at a glance, what you want to do when you design something for FPGA or design hardware is you want to optimize your computation and your memory accesses so that you're keeping all parts of the circuit active at all times. So if you're going to spend resources putting some part of a circuit on your design, you want to get the most out of that by having it active all the time. In order to do this, there are some things that you can make decisions about as a designer. These are parallelism, data locality, and control flow. So these are kind of three knobs that you have access to as a designer. So adding parallelization is going to spend resources to run your application faster. Controlling data locality, this is because on FPGAs, you typically don't have a cache hierarchy in the loop for you, so you have to manually manage how you access and store data. And control flow, since you are designing a hardware circuit, this is how you control or how you create contracts between different loops in your code and how they're going to execute relative to each other. So Spatial is an open source language, and it exposes these knobs, which you're going to see in a moment. And exposing these knobs creates a big design space problem. So HyperMapper is there to help us along the way. So looking at what Spatial provides, we're going to look at kind of the syntax and what it exposes. So here's a quick summary, kind of preview of what the syntax looks like, and we're going to talk in more detail about each of these components. But the first thing is it exposes parallelization factors. So if you look over on the right, here's a snippet of spatial code, and in green here, there is a parallelization factor called P, and we're saying that we want to run this loop, which is going to run for n iterations at some parallelization factor. There are explicit and implicit control schemes. So here you can annotate certain loops in Spatial to have certain schedules. In this case, it is a stream controller. We'll talk about this more in a moment. And there are explicit tile sizes that you can expose in your application. So in this case, B is a tile size. Since when you design hardware, you need to know your tile sizes statically at compile time so that you can size your on-chip memories. And then you also need to use this information for your control flow in the application. So in this case, you're going for n iterations, but you're stepping B increments each time. And then finally, there's implicit memory banking and buffering, which we'll talk about. And banking and buffering are basically the things that consume resources when you design hardware. So you want to get better performance by adding parallelization. Banking and buffering are going to be kind of the trade-off there, and they're going to consume more resources. So the HyperMapper tool or whatever is optimizing this has to be aware of what's going on. So taking another step back and looking at Spatial at a very high level, It's based on parallel patterns. Parallel patterns are loop abstractions with implicit information about parallelism and how you access your memories. So a few quick examples to give you a mental image of parallel patterns. There's a map function, which is when you take a collection and create a new collection with some element-wise function. There's a reduce pattern, which is when you take a collection, reduce it into a scalar with some associative function. And there's also zip, which is when you take multiple collections, combine them element-wise to create a final collection. And there's a few other patterns, but these are kind of the biggest ones. So spatial is an imperative language, but it's designed to easily capture these patterns. So if we look at in spatial, you are going to write loops and you're going to nest these loops. If we look at what that actually means in hardware, when you have a loop in your software, it creates a counter chain with a controller. A counter chain is just a collection of iterators that are chained together that define the stepping order, and they're going to be hardware counters. And then your controller is your container for some data path of operations or circuits, or it's going to be other controllers. If we look at that in a little more detail, because controllers or loops are going to be nested throughout your application, this gives us the definition of inner controllers, which are these loops that contain only primitive nodes. In this case, primitive refers to things like arithmetic, memory accesses, muxing, and things like that. If it contains other controllers or other loops, then we call those outer controllers. And these are the controllers that each of the children we call, or each of the loops inside of an outer controller we call a child. So to give you a quick example of what this looks like, here we have 3 loops. We have the parent loop, which is an outer controller, and it has 2 children. Each of these children, if you look at what's going on inside them, you can see it's only primitive operations, arithmetic, memory accesses, and stuff like that. So a minor detail in spatial is if you have some primitives that are floating alongside other controllers, the spatial compiler has a pass that is going to wrap those in unit controllers so that this paradigm holds true all the time. If we look at this in terms of performance, which is ultimately what we care about at the end of the day, and the reason why you want to run DSE on your application, what you want to look at is how this loop is going to consume cycles when you run it. So on the left here, there's just some sterile example of a loop. It's going to run for 5 iterations. I'm telling you the latency and initiation interval numbers here. If we look at what that means in how this unfolds over time using a waveform diagram, where we have time on the horizontal axis and iteration on the vertical, what's going to happen is at time 0, whoever is the parent of this loop is going to receive an enable signal. This enable signal is going to kick off the execution of this controller, and it's going to look something like this. So it's going to run for its 5 iterations. When it is finally done, it's going to send the done signal to the parent. If we dissect what happened in this diagram, you can see the latency is how long it takes for one of these iterations to complete. Initiation interval is how long you have to wait between kicking off a new iteration. And the equation that binds all these quantities together is shown here. It's not too complicated, but it ends up being really tricky when you think about how all these loops are nested. So you could plug into the equation here to get the total runtime of this controller. There's always going to be a little bit of overhead for communicating these signals to and from the parent. So the reason I went into detail of that waveform diagram is because an important feature of spatial is understanding the schedules of outer controllers. So an outer controller, as I mentioned before, is a controller that contains other controllers as its children rather than pure data paths. There's a few schedules that these can take. So I'm going to list 3 of them here. There's a few more, but these are the 3 main ones, kind of the workhorses of the language that do most of the work. So the first one is sequential, where you have no overlapping of the children. Next is pipeline, where you do have coarse grain overlapping of the children. Think of this as kind of like a memory prefetching if you're thinking of CPU world. And then there's streaming, which is data-driven execution of the children. So the parent kind of steps out of the way, and the data dependencies between the children of the controller are what drive their execution. For the most part, sequential, or all the time, sequential and pipeline are interchangeable without rewriting the code. If you want to use a stream controller, you typically have to do a little bit of rewriting, but these 3 schedules all kind of serve the same purpose in the language. If we look at what these controllers mean for performance, starting with the sequential controller, which is the most straightforward one, we're going to look at a waveform diagram of this. So here we have the same waveform diagram with time on the horizontal axis in each stage. In this case, there are 3 stages. a load stage, some compute, and a store stage. And I just want to mention that in spatial, load and store are kind of nice, clean API for handling controller subtree that is going to communicate with the DMA to fetch data and return data to the accelerator. If we look at how this unfolds over time, a sequential schedule says that it's going to unfold this way. So you're going to run through each iteration. Sorry, you're going to run through one iteration of the parent controller per stage. When that final stage finishes for the first iteration, then it could go back to the beginning and kick off the next iteration for the first child. So if we compare, before we talked about latency and initiation interval. For outer controllers, they're kind of tricky concepts to nail down because you don't always know them at compile time. In this case, we have some loads and stores, which are going to be runtime dynamic because those talk to DRAM and the DMA. So you don't actually know these quantities, latency and initiation interval beforehand, but you can make kind of effective estimates of what they are. If we look at a pipeline schedule, and in spatial, pipeline is going to be the default schedule. If you're not running DSE and you don't annotate it, every controller that is an outer loop is going to have the pipeline schedule. If we look at how this unfolds over time, it's going to look like this, where you can see there's the coarse grain overlapping of the stages. So if we look at the first, the load stage, it's going to run for iteration I equals 0. As soon as it's done, it's going to advance to iteration I equals 1, while its downstream later controllers are going to execute. In this case, the effective initiation interval is going to be smaller because when we are running in steady state, it's the bottleneck stage that determines this quantity. And finally, there's a stream controller. So if you look, we had to rewrite the code a little bit to use FIFOs. FIFOs are basically queues that are communicating data between the stages. If we look at how this executes over time, you can see that because everything is going to execute as soon as it has data available to it, the effective latency is going to be smaller. The effective initiation interval is going to be the same as the pipeline schedule above it. So a few things I just want to call out real quick. In this case, if we're looking at the pipeline schedule, steady state is when the pipeline is full. So the equation that I mentioned before, where you look at initiation interval, latency, and number of iterations, if the thing runs in steady state for a long time, that's when that equation holds most true for these outer controllers. And a few things in the stream waveform that I want to call out are because this is driven by FIFOs, the FIFOs might fill up or they might be empty. So if a FIFO is full and somebody is trying to enqueue data to it, it's going to cause a stall. So in this case, we're loading from DRAM into a FIFO. When that FIFO fills up because the next stage is not dequeuing fast enough, that's when you get this bubble in this execution. And then for someone who's consuming from a FIFO, if that FIFO runs out of data, then you get into a situation where it is starved and has to wait for more data to appear. So I went into a lot of detail on how all these pieces fit together. So I'm going to tie it up real quick with this example, some arbitrary example of loop nesting, so that you can see that trying to figure out how to balance your pipeline can be kind of tricky. So the way you think about performance in this case, we have a parent controller that I'm giving a sequential schedule. So as you saw before, this is what the sequential schedule might look like. If we look at the first child and zoom into this first box, it's going to be its own intercontroller with its own execution. If you zoom into the next box, that is by default going to be pipeline schedule. Since I'm saying that it contains other controllers here, this is what that execution is going to look like. And finally, the third stage I'm saying is a stream controller doing some work, and it's going to look like this. So the problem here is how do you choose the right parallelization factors and tile sizes so that at the end of the day, you are minimizing the runtime of the parent controller without blowing up your resource budget. So in terms of resource budget, one of the things that is going to run out when you're designing these applications might be your memories on chip. So the memory hierarchy on an FPGA looks like this. There is your DRAM, which is gigabytes of data, and it resides off chip. It's going to be allocated by the host, the CPU, dynamically. But then below that, you have your on-chip SRAMs and your on-chip registers. And these are the things that you have to be careful about using. So looking at what spatial code looks like when you are using these different parts of the memory hierarchy might look something like this. So you could declare some DRAM. there are different ways of declaring on-chip SRAMs that have different contracts with how you access them. So here we have FIFOs or line buffers. There's syntax for getting the data from DRAM to on-chip and then on-chip back to DRAM, as you saw before. And these are going to be their own controller sub-hierarchies that handle this communication with the DMA. And finally, there are your registers, which are your single element resources that are on-chip. The last thing I want to talk about for memory and why resources are going to get consumed based on your design parameter decisions is buffering. So buffering is the implicit duplication of memory, and this protects different parts of the memory from each other, particularly in a pipeline controller schedule. So what that means, let's look at just a very simple piece of code here. We have a parent controller who is going to have a pipeline schedule, again, because there's no annotation here, so pipeline is the default. And then we declare some memory. We have 3 children stages, and we access the memory, we write to it in the first stage, and then we read from it in the third stage. The compiler, kind of giving you a shortcut here, but the compiler is going to analyze this and see that it needs a triple buffer to implement this properly with the pipeline schedule. And the reason it needs to do this is because when this unfolds over time, you're going to see something like this. So this parent controller is going to kick off iteration I equals 0, and it's going to store its data to the first part of the buffer here. When that's done, we can increment that counter. It's going to store data from I equals 1 to the middle buffer. And then finally, we increment again. It's going to store data from I equals 2 to the third part of the buffer. And under the pipeline schedule, this is going to be the first time where this third stage is going to be active, looking for data for iteration I equals 0. If you look, we triple buffered, so that data is still here in the first part of the buffer. So this code is going to run, and every stage here is going to be happy with the data that it receives. And then once that's done, we increment again. We don't need data from I equals 0 anymore, so we could overwrite it with iteration I equals 3. This is going to be done implicitly by the compiler, but this is one of the reasons why if a particular part of your application is not the bottleneck, by having a pipeline schedule, you're going to consume more resources, and it's a trade-off of, do you actually need that extra performance for that particular stage? Or can you get away with using a sequential schedule where you don't need to triple the amount of resources that you're using, for example, in this case? So to wrap it up, there is the trade-off between resource utilization and performance. So you want to add parallelization, you might want to increase your tile sizes, and you might want to use pipeline schedules to get better performance. And all these have consequences on the resources that you're going to be using. And on FPGA, these are your memory, logic, and DSP resources. These trade-offs, sometimes they're simple to understand, but when you start doing complex applications from real domains, like maybe machine learning applications or networking applications or genetic alignment type of stuff, these trade-offs become really complicated for a human to understand, and this is where HyperMapper comes in to help you out. So that's just a quick preview on Spatial. I'll take any questions now. I saw some notifications. People might be typing questions, but we can talk a little bit more now if anyone wants to ask anything.
Yes, thanks very much, Matt. This is a good time to ask questions on this presentation of Spatial. There will be more on Spatial right after this with the demo that Matt and Artur will run. But this is a good time to ask questions if there are questions around.
We have a question, David Durst.
Hi, yes. Hi, Matt. What is the difference between the hardware generated by the streaming and pipeline schedules?
Okay, yeah, so your question is the difference between the hardware when you're using the 2 different schedules. Let me share the screen again real quick. I turned it off so you're not looking at my blank Zoom screen, but it should be back on now. Let me get to that. So the main difference is the protocol of how things execute. So the enable signals for these controllers is going to be different under the 2 schedules. So I think you could see this now. So in the case of a pipeline schedule, even if we had FIFOs here, the contract for a pipeline schedule is that all the enable signals get aggregated. All the enable and the done signals are aggregated by the parent. and that the parent is going to be the one who drives each of the children. So if you look at the waveform diagram, they always, each iteration or each the enable signal that kicks off each of the children happens at the same time. This is because the parent is controlling it. In the case of a stream controller, the parent just kind of steps out of the way. And in terms of hardware, what that means is that each of these children now needs their own copy of the counter chain of the parent. So because there's no kind of synchronization or kind of master taking control of the execution, we need to copy the counter chain for each of the children so that they know what iteration they're working on. And we also need to have the enable and done signals kind of routed all throughout and between the children to manage their execution.
That makes a lot of sense. Thank you.
Great. I think there is another question that's being asked on the chat. That means that if there are no other questions, we can maybe move on the next session.
Okay.
Just wait maybe a couple of seconds just to see if.
Oh, I see
okay.
a hand.
This question here, how to talk.
Oh, sorry. I clicking around on Slack, and I think I just there. Okay.
Does Reika, right?
Yes.
Do you hear me?
Yeah,
yes.
I hear you.
So you mentioned that increase and decrease of tile size will impact your performance. Well, I don't know what a tile size or what a tile is, and how do you spell it?
Okay, yeah. So we're going to talk about that a little bit more in the demo that we're about to look at. It's going to be a lot more concrete and hands-on. But
okay,
quick answer to the question. Yeah, so tile size, to answer your question real quickly, tile size is how you size your on-chip memories. So I mentioned previously that the DRAM is going to be allocated dynamically by the host, but when you are designing your hardware and putting something onto the FPGA, you need to know exactly what resources to allocate because you have to bake in the bit stream for the FPGA. So you need to lock this in.
Yeah, so sorry, in the middle of your talk. So is tile is it a software or hardware component?
Tile size ultimately becomes a hardware parameter.
What tile itself is a hardware. Tile itself is a hardware, but we can modify the size with software.
Yeah. So when you're using Spatial, you're writing the software so you have access to mostly typical Scala syntax, and you can actually use your tile sizes outside of the scope of the hardware. But when I'm talking about tile sizes in the context of DSE in domain space exploration, what I'm talking about is when you make a choice on how you size your tiles, how you actually declare the parameters. So in this example here, we have buffer.
I have a problem. So size is clear, but what a tile itself? What is tile itself? So size is fine, but like, what is a tile?
Right. Sorry. So tile, that's just the word that kind of we use colloquially when talking about Spatial for something that resides on chip. So you'll see some examples in the next talk.
Something special on a chip means a tile, like a unit on the Spatial chip means a tile.
Sorry, can you repeat that?
But still, a unit, as example, unit on a Spatial chip is a tile, right?
So the tile sizes that I'm talking about refer to actual like parameters. I just want to be clear about a unit. In Spatial, I guess a unit could refer to kind of a loop or a piece of.
Matt, if I can intervene very quickly. I think you have a very good example of what a tile is in your next presentation. And I see that also David is asking this a similar question here. So I think in the very first like 2 or 3 slides of your next presentation, you will talk about tiles, right? Isn't it?
Yes. Yeah.
Yes. So maybe we can deal with those tile questions at that time if you don't mind.
All right, thank you. Absolutely. Thank you.
Great, thanks. There is also another question by Jeff. I can read the question if you want, or Jeff, you can actually ask it yourself. What do you prefer? I'll probably just read the question.
Okay.
And Jeff is saying, in terms of functionality, what are the differences between spatial and those HLS tools?
Yeah, so in terms of functionality, there's a few differences. Spatial was kind of built ground up with the idea that if you were designing hardware, you should have some sort of hardware syntax rather than slapping pragmas onto C to fill in the gaps for hardware. So if I understand correctly, the question is, what is the difference in expressibility? Spatial is going to give you explicit CPU host code versus what goes on the accelerator. It's going to give you explicit control over how you manage the memories. So how you transfer to and from DRAM and on chip, whether that's going to be dense transactions or it's going to be scatter, gather, kind of sparse transactions. It's also going to give you control over, so when you're actually designing your code, it gives you debugger tools. So you could look at the performance of your application in a fine grain and also coarse grain way to figure out where the bottlenecks are and where you should spend your attention when you're designing the application. So there's a few differences. They do kind of serve the same purpose, whereas you want to write high-level language in a general purpose way and put that on the FPGA. But there's differences when it comes down to the details, how you implement things and how you understand what your code is actually doing.
Great, Jeff. I hope this answers your question. If it doesn't, please raise your hand again and we'll let you in and ask more clarification. There is another question on Slack by David. What's the difference between the hardware generated by pipelined and streaming schedules?
Yeah, that's the one that we got verbally.
Oh, sorry. Sorry,
Yeah.
I didn't. Okay, great. So at this point, any more questions? Okay, great. So maybe we can move on. This is the demo on spatial with a flavor of HyperMapper. Please, Matt, go ahead.
Okay, so this is Matt talking again. So we're going to look at the concrete how you integrate spatial with HyperMapper, and we're going to use general matrix multiply to kind of drive this discussion. So if you haven't already, you can go to the HyperMapper wiki, go to the spatial use case, which is going to tell you everything you need to know about running spatial and HyperMapper together. But you can also just kind of sit back and watch if you prefer to do that and kind of watch how this works when I do it for you. So I'm going to try to go slow so that if you want, you can follow along. I think the link is already posted in the Slack channel. So I'll move on. So we're talking about general matrix multiply here. I want to start off with showing you kind of what that looks like and how do you map matrix multiply to hardware. There's hundreds of implementations, maybe not hundreds, but lots of people are interested in this problem because matrix multiply is a fundamental linear algebra kernel. In this particular example, we're going to multiply A times B to get some answer C. And you can see the dimensions of these matrices in the subscript. And I want to point out that these are things that are going to be allocated dynamically at runtime. So the CPU who kicks off the accelerator or the FPGA is going to know what these dimensions are, and it's going to allocate DRAM based on those sizes. So in order to solve this on the FPGA using our accelerator, we need to use tiling. And in this particular example, I'm going to show you inner products, but there's lots of other ways of doing this. You could use outer products. You could do systolic arrays and other implementations. But for our purposes, we're going to use inner products. So here, as I mentioned before, these are your matrices. These are the data structures that are going to be allocated by the host dynamically. These are the dimensions that I'm calling out. And so the question in the previous talk about tiling, when I was mentioning tile sizes, what I mean is you can't actually fit the entire DRAM on chip. You have to do some sort of tiling so that you could support any dimension matrices. And what I mean by tile is these black boxes called tile A, B, and C are going to be the things that actually reside on the FPGA. As you'll see in a moment, these are the things that you have control over and you might want to feed to DSE or HyperMapper to figure out the best choices for them. So if you're doing a matrix multiply, you're going to produce tile C is going to be a partial result. To get the full result, you need to step and get the rest of the portions of A and B that contribute to that portion of C. When you're done, you're allowed to increment, and you now produce the next result, or partial result for tile C, which has moved in the memory space of C. And you're going to step forward and compute the complete result before you can move on. So that's how that works, but let's look at what's going on inside the accelerator and what is actually happening inside of these tiles to perform the matrix multiply. If we do that, we can see, because I'm saying that this is going to be inner product implementation, these tiles are going to contain elements. To produce a result for tile C, you need to do a dot product between a row vector in tile A and a column vector in tile B. And then we can proceed and step forward to compute the entire tile. So in just these simple cartoons, which you've probably seen a lot of times before or thought about in your own work, there's a few obvious design choices when we map this to FPGA. So first thing, as I mentioned, is tile sizes. This refers to how big do you want your on-chip tiles to be. So you're going to get the best performance if you have large tiles, and this is because you want to have large, dense transactions with DRAM. So bigger tiles means you have longer requests, but you're going to consume more resources if you have bigger tiles. There is parallelization at the tile level. So this is where you can multiply or compute multiple columns or multiple rows at a time. And these are independent of each other, so you could scale them to any parallelization independently. There's also this level of parallelization where you work on multiple tiles at once that contribute to the same partial result of C. The reason I grade this out is because if you've already cloned that repository and looked at the code, I didn't actually expose this level of parallelism. You need to change the spatial syntax a little bit, but this level of parallelism is still a thing if you change the implementation slightly. So looking at what's going on in the tiles, you have more choices. There is the parallelization of your inner product. There's how many inner products you want to compute at once, and this exposes two levels of parallelism for tile A and tile B. And so at a glance, these are the things that we just talked about. There's obvious design choices when you think about the problem in kind of that cartoon scope that we just looked at. There's also some less obvious design choices. So in the previous talk introducing spatial, we went into a lot of detail about outer controller schedules. In this case, there's a trade-off between sequential and pipeline controllers, and we'll look at that more in a moment. And also in the cartoons, it wasn't obvious, but there is DRAM transfer parallelization. So this is referring to how many elements you consume off the DMA bus per cycle, and that's also a design choice. So I'm going to throw up the code here. You don't have to pull it apart right away. This is the entire accelerator that is going to do the matrix multiply. If you clone the repository and looked at the example already, you'll see this exact code already there. But to tie this in with what we just talked about, the stuff that is not grayed out right now, this is the stuff that is managing tiles. So this is the part of the code that is going to allocate your on-chip tiles using some parameters, BM, BP, in the case of tile C. And then you can see the loop structure here is what is going to step through the problem. Now, the stuff that the other part of the code is what handles what goes on chip. So this is the part that actually does the inner products. So there is the loop that steps over in dimensions N and P. And then there's also the inner product, which is shown here as a reduced controller. And that's the thing that's going to accumulate the inner product. So if we look at what design choices you have in this code, there's a ton of them. Some of them are repeated. So for example, BM is going to be a step factor here, and it's also going to be what sizes your on-chip memory. And so there's a lot of these choices all throughout the code. And I'm not showing you yet where I declare these. I'm just calling out that these things are design parameters that either you have to choose as a designer or you throw to the DSE tool like HyperMapper to solve them for you. And then there's also the implicit tunable parameters. In this case, there are 3 outer controllers. And this, whether they're going to be sequential or pipeline execution, is a choice that is going to be exposed to HyperMapper or the DSE tool. And so GEM, the nesting here is not super complicated. It is nicely nested with just one outer controller here, but there's other applications where this could be very wide, it could be very deep. This is just one use case that I'm trying to show where I can expose a design space and let the tool explore it for me. So now I'm going to show you how I declared those design parameters that I just called out before. So specifically, there are your HyperMapper integer parameters. So if we look at just BM up here, we're saying BM is going to be 16 by default. If you're not going to run DSE, this is actually going to be what gets baked into the hardware. But this is a DSE annotation in parentheses. And that's just saying that this parameter can take any value from 1 to 128. I want the tool to figure out which one is the best choice for me in the context of all the other ones. Next, we have our parameters that we can declare with a step size. So rather than taking every value from 16 to 1028, we're saying that we want it to only be in increments of 16. This is your HyperMapper ordinal variables. And you can also declare explicitly what values you want it to take. So for the load and store parallelizations, you want to choose these so that they evenly divide the burst width of whatever FPGA you're using. So we don't want it to take any value. We want it to take only these powers of 2, because those are only going to be the parameters that are actually valid when you put this into hardware in Spatial's current implementation. So another thing is, as I mentioned before, there are the host code parameters, the things that are dynamic. In this example, this is the dimensions of your matrices. And for the sake of DSE, there's going to be a runtime model. Since these are dynamic, you want to give it a kind of an estimate to use for the sake of DSE of these parameters. So here I'm just declaring M, N, and P. For the sake of modeling the runtime, I want the tool to use these parameters. So if we look at how HyperMapper and Spatial actually integrate, what I showed is that you can have a huge design space, especially if you're not careful about winnowing down your choices. HyperMapper lets us explore it intelligently. So Spatial compiler, Luigi showed a more detailed example. This is a less detailed example. There's a lot more passes in both of those cases. If you want to see what Spatial is doing, you could dig into the source code. But for the most part, there's some lowering, there's the DSE pass, and then some stuff that happens afterwards. What I want to call out here, though, is the DSE pass. So DSE, I alluded to this before, there's area and latency models. These are based on spatial IR nodes, and there are models that will estimate how many BRAMs, slices, and DSPs certain nodes are going to take relative to the parameters in the IR. And it's going to add those up to give you top-level estimates. And this is going to talk with the HyperMapper process, which is going to be spawned automatically by Spatial. And there's going to be a feedback loop where the two kind of negotiate to find the best point in this DSE space. And I mentioned before, we use XGBoost models to model the spatial IR for the sake of area. Someone asked this on the Slack, I think, on what happens if you don't have models or you don't have a quick feedback loop here. So in this case, what I'm showing is you can't have a quick model. You need to go all the way through the compiler, through CodeGen, and all the way past synthesis before you can return some result on runtime and resource utilization. So we haven't laid down the plumbing yet in Spatial to do this, but if you're thinking about how to apply HyperMapper to your own task, this is definitely a valid configuration, and HyperMapper is a good candidate for this because, as Luigi mentioned before, you can search the space very efficiently and not require too many iterations to converge on a good point. So I've practiced this a few times, but now I want to show you a live demo of how all these things fit together. So I'm going to switch over to some terminal sessions to show you how this actually works in real life. So actually, I'll take questions if anyone has any questions right now. Okay, so it doesn't look like there's questions.
I think we have two questions.
Now. Okay.
Hampus, do you want to ask that? Let me.
Sure, I can ask it. So I was just wondering, in your code example, you showed that you could have an additive increment to decide that you only want to increment it by 16 or so.
Yes.
It seems like it would be natural to have a similar thing for multiplicative increments rather than relying on the list you have in the bottom of the slide.
Yeah,
that's a good point. There's no syntax, but I could add that syntax pretty quickly. That's a good point.
It just seemed like a design choice you would want to have in your language.
Yeah, definitely. I'll make a note of that. That's a good point.
The other question is by Claire. Sorry, it seems that the gem. Sorry, what's the question here? I think the question is not complete. Clark, would you like to ask the question verbally?
I just found a Q&A feature in Zoom, but I can't find the actual chat where these questions are being asked.
I see. It's on the bottom, the center. There's a chat.
Hi.
Okay, there.
Hi, Clark.
Yeah, hi. I tried to execute the example before you already start the live demo, but I couldn't execute the one because of the error I posted on the chat. It says Java. Yeah.
Can you pause the error, because what I'm seeing here? Oh, Java lang runtime exception, right?
Yeah, / package cannot be represented as URI.
Oh, the URI thing.
Yeah.
If I recall, this is related to SBT version or Scala version. If you post it on the, if we talk on the Slack, I could help out with that. Or if anyone else is running into that and knows how to solve it.
Okay.
Yeah, this URI thing. So if it's okay, I'll go look at my notes. I know I've run into this one before, but for now I'll move on and show how this works in the command line if you don't actually get this error, if that's okay.
Okay, good.
Okay, so everyone should be able to see my screen now. Let me make this a little bit bigger so that everyone can see more clearly. Okay, so what I have here is a just clean directory. And the first thing I want to do is clone the spatial repository. So that is going to be Stanford PPL/spatial quick start. There's also a spatial, not quick start. That's going to be the full compiler. For this demo, you don't actually need that one because we packaged everything as a jar that we published, which is what quick start is. So we're going to move into quick start. You can see it's pretty minimal. There's not much here. First thing you need to do is get on the DSE branch so that you get all the DSE stuff that we talked about. And then you also want to update the submodules, which is going to fetch the XGBoost models for area that I talked about before. So that'll take a second. So we got that. And I also just want to set my spatial home variable in case we need that in the compiler.
Matt, perhaps we can slow down a little bit here so that everybody can. I think we are on time, so just maybe let's wait a few seconds so to make sure that everybody's on the same page. Can you maybe show a history of what you typed so far?
Yeah. So if you look at what I've done so far, I'll slow down a little bit, but we have our cloning quick start, and then I moved into it so that I could get on the DSE branch, and so I could get the submodules, which in this case is just the area models, the XGBoost models that are going to be used for estimating area. If you're working from true spatial compiler, meaning the spatial repository and not spatial quick start, there's a bunch of other submodules that are going to come along for the ride. For our purposes, the modeling stuff is all we need here. And then I'm setting the spatial home variable to current directory. So in terms of spatial installation, that's really all we need to do.
All these comments, Matt, are basically, you can just copy paste them from the wiki, right? Can you show the wiki again, please?
Yes. You mean actually go to that website?
Yes, the GitHub.
Yeah. There we go. So for now, I'm following this part of the wiki, which is all the stuff related to spatial. So all this stuff assumes that you have these dependencies installed. So if you haven't used Scala or SBT before, that's probably the big one. So you just want to get SBT. If you're running Linux, you could just install SBT this way. And the other thing is integer set library. A lot of people don't actually have that right off the bat. So you also want to get ISL. So that's used in Spatial's banking analyzer. Probably the most common error in Spatial is it crashes because of ISL not being found. If you get that error, we could talk about that, or if you search in Google, you should be able to find the solution. Real quick, the solution, the easiest way to get past it is make sure you have ISL installed, and then you can just manually compile the binary that you need to use ISL for and put it on your path. So you'll see answers to that particular question if you run into an issue with ISL. So at this point, we are done with the spatial stuff here. Let me move this so that you can see it all together.
Great. So maybe this was a good break if anyone had to catch up with what was happening here, but we can keep going now.
Okay. So now
Thanks.
Let's pretend that I've never seen HyperMapper before. So I'm going to clone HyperMapper real quick. This is not in this particular wiki, but this assumes that you've already followed the other HyperMapper tutorials. But I'm just going to do that real quick here. So now I just cloned it. I'm going to walk into it real quick to look at what's there, and also set my HyperMapper home variable, which it says to do here, so that it knows where to find the Python scripts that call HyperMapper. So that's all we need to do for HyperMapper. I'm going to walk back to Spatial Quick Start directory. And now we're actually going to compile our application, which in this case is gem that we talked about in the slides previously. So the command that we run is bin spatial. So this is a script that is going to do all the SBT Scala package stuff for you. You could also use SBT directly if you want. You could get into a term or SBT console here. But that involves a little bit more knowledge of how SBT works. So we're just going to use bin spatial. That's going to take care of all that stuff for us. All we have to do is give it the application we want to run, which is gem. So real quick, all the applications in the Spatial Quick Start repository live in this directory source right here. So if I list what's there, there's two files. There's gem and hello spatial. This gem is specific to the DSE branch because this is the tutorial for showing you how to integrate DSE. I'm just going to real quick open this file up so you can see what's here. And at the top level, we have this macro spatial object gem. So this is the application that we want to call with bin spatial. I'll go back to that in a second, but I'm going to get this command running because we want DSE to kind of cook for a little bit. So I'm going to run gem. I'm going to tell the compiler that I want to run DSE, which is tune. And the particular tuner I want to use is HyperMapper. And I want to set some HyperMapper parameters here. So the two that I really want to set, as you can see in this tutorial down here, is the design of experiment samples. So this number of random samples that you want it to kick off with. And I also want to tell it how many iterations I want it to run for. So that this doesn't take too long, I'm just going to run 16 for this demo right here. And then I also want to tell it what FPGA I'm using. So the way to do that with the bin spatial script is telling it synth, meaning I want to ultimately get a bit stream or RTL code out of this, as opposed to sim, which is just going to be Scala simulation. And I also want to tell it what FPGA I want to use. In this case, I want to use ZCU, which is the Xilinx ZCU 102 FPGA. And that's what these models are based on right now. And so this is the entire command that we want to run DSE on this gem. So I'm going to get that started. When you run this, if you're not familiar with SBT, for the first time, it's going to fetch a whole bunch of packages from the internet, which is what's happening here. All of this, these lines are going to appear and disappear until it has all the jars and everything that it needs. So while this is going, I'm going to pull back this window here so we could look at the application in a little bit more detail. So on the bottom there, you can see that's just going to continue running. We actually got to the point now on the bottom here where it's going to tell you what the design space is for this application. So if you look at these numbers, they're probably going to be familiar. These are the choices that I mentioned previously. They're a little bit different. I changed the example last minute so that it works nicely for this tutorial and doesn't take too long. But yeah, these are the parameters. So let me pull up the application on top here so you can see. So scrolling down a little bit to the important stuff, all the stuff that I'm flying by right now, this is stuff that runs on the host. This is stuff that is going to allocate your DRAM and set up some data to run matrix multiply on. But the thing that we care about is the DSE part, which here is where we are declaring the ranges and values for these parameters. This is outside of the Excel. So we're declaring these up here. If we jump down a little bit, this is where we start the Excel. So everything that is in the Excel brackets here, we're saying in Spatial that this is going to be run on the accelerator. So this is meaning the FPGA. So if we look at the bottom, I just want to show you this line here. So it finished compiling the DSE model. This means the latency models and the area models on the Spatial IR. So now it's going to run that feedback loop with HyperMapper. It's telling us there's 13 parameters. And if you look at the ranges and take the volume of this design space, in this particular case, it's 29 billion points, which we definitely can't do exhaustively. So this is why we need HyperMapper in this case. So this code up top here, this is exactly the application I showed you in the slides. This is your matrix multiply. And then below that, outside of the Excel, if we scroll down a little bit, this is, we just do a simple check to make sure we got the correct answer. So this is an entire Spatial application. If you want to try Spatial plus HyperMapper, you could feel free to start from here. Or if you go back, you could look at Spatial Quick Start, which is, Hello Spatial, which is the other application that ships with Spatial Quick Start. This should give you a good rundown of all the kind of different pieces of syntax you have in the language. Or you could go to the Spatial website, which I think you could get linked to on the PLDI program. And that'll give you more documentation on how to use Spatial. But hopefully a lot of people are here because they have their own project and huge design spaces that they want to explore themselves. So they want to use HyperMapper to do that. This is just one use case. You could see a working end-to-end solution of HyperMapper talking with some external project. So on the bottom here, this is still running, but because this might take some time, I did this in advance. So I'm going to show you what to expect when this finishes. So when you run Spatial applications, it's going to put some in the quick start directory again. It's going to put your generated code, all the stuff, the chiseled RTL and the host code that gets generated is going to land in this gen directory here. So if we look at it, we have a directory per application. In this case, it's only gem. So what I'm going to do is show you what this directory is going to look like after all this finishes. You're going to get something like this. So what you're looking at here, if you look at just the directories in blue, we have some information on banking. The important stuff is chisel and CPP. This is kind of the payload that you get out of the compiler. Chisel is going to be what turns into Verilog and runs on the FPGA. CPP is going to be the stuff that you specified runs on the host. The communication between the two is going to be handled automatically by the plumbing that Spatial gives you by default. And the thing that we care about for the sake of DSE is this file up here called gem output DSE samples.csv. If we look at what's in here, this is just a CSV of all the points that it tested and how they all did. So it's a CSV. The columns of each of these are defined as the first line of this file up here. They're kind of scrambled in order here, but the outputs that we care about are cycles, which is this column here. And we also care about slices, the way that HyperMapper is set up. And you could change this at the Spatial command line. We want to look at the trade-off between cycles and slices. And we only care about the points which are deemed valid, meaning they actually fit on the FPGA, which is this column here. So Oh, okay. So down here, it just finished. So this is what the directory is going to look like, fresh off of a compilation. I'm going to move that to the top. So let's go to it. So this is your generated directory. Here's your DSE output. Now, what you might want to do is look at Pareto frontier for this particular application. So in order to do that, we have to go to the HyperMapper directory. So now I'm in HyperMapper. It's just a fresh master branch of HyperMapper. And there's a few scripts that we want to run. First one is going to be the where is it? Compute. It's going to be in scripts. And it's a script called compute Pareto. And the only argument we need to give this is this JSON that got passed to HyperMapper. So I didn't talk about this before. I forgot to mention it. But in Spatial Quick Start, when you run HyperMapper DSE, you're going to get this DSE HM directory. And that's going to give you the JSON config for HyperMapper. So this is kind of contains all the information that HyperMapper needs to do its thing. So we're going to run compute Pareto on this file. It's going to take just a second. And so now we want to plot this as a Pareto frontier that we can look at. So we run another script in HyperMapper scripts directory called plot DSE. And we also give it that same JSON as before. And that's going to take a second. It's going to produce a plot in this directory here, which is our output directory. So I'm going to jump over there real quick. So Spatial Quick Start gem, and this is where it dumped the output. So you can see there's a few more files here. The one that we care about is this PDF here. So if we open and look at what that looks like, this one didn't look as clean as before. Probably should have run for more samples, but let me do the same thing over here on this one that I already ran previously. So if you run that same, if you open it up and look at what's in that PDF. Oh, wait, whoops, yeah, I opened the wrong file. There we go. Sorry about that. So this is the Pareto frontier for the application we just ran. So,
and perhaps, Matt, perhaps we should mention the fact that the Pareto frontier will be introduced. So this multi-objective optimization problem would be introduced a little bit better in the next session with Artur. But maybe for now, it's enough to understand that the Pareto frontier is a trade-off between these two different objectives here.
Right. So I mentioned before, what we care about is the cycle count and how many logic resources we're using. And so just dissecting this frontier a little bit, the key thing to see is that you can pay more logic to get marginally better runtime. So in the case of cycles, lower is better. In the case of logic utilization, lower is also better, but as long as it fits on the FPGA, you should be good for your application. There might be reasons why you want to actually minimize logic utilization. That might be for power reasons or because you're sharing the FPGA with some other applications. But the trade-off here is you can pay more of this to get better results of this. So that's all for the demo. So if anyone has questions, I could answer them, or I could jump on Slack and talk with some people and get back to the person who asked about URI.
Thanks, Matt. I think there is a question on Slack. It's a technical issue on Spatial. So maybe right after this, you can help. I think it's Jeff asking that question. And perhaps before wrapping it up, can you please go back a little bit to the JSON explanation the JSON file that you mentioned before? Can you maybe no, the one that is in your shell? So I think you were showing the JSON file that is automatically generated by the compiler. Can you tell us a little bit more about that? What's the dynamic there?
Sorry, I just want to make sure I have the right one. You're talking about this one, the JSON config for HyperMapper?
Yes. Yes.
Yeah. Yeah, so this JSON is setting up the HyperMapper configuration. So not all the knobs in this JSON are going to be exposed by Spatial right now. These are things that I'm continually adding as people need it, but there are a few that you can configure. So brief rundown on what this JSON is is it sets up the experiment for spatial. So what that means is, let me skip over to the ones that we actually tuned in my example. So one that we actually tuned was design of experiment. So this is the first thing that HyperMapper does, is get a sense of the space. And if you remember in the command line, I told it to do 14. And the reason I chose 14 is because I knew that this example, this gem has 13 parameters. So typically you could choose one more DOE sample than the number of parameters that you're trying to tune. And then another thing that is important here is that this JSON calls out how many iterations, optimization iterations, which we set to 16. In real life, I'd probably set this higher so that I could get a better view of the space. So if you're trying to integrate HyperMapper with your own project, you'll probably spend a lot of time getting your JSON set up just right for your purposes.
Yes, and so perhaps we should also add that this JSON here is automatically generated by Spatial. So when Spatial compiles, it will automatically generate from the high-level program. It will automatically generate this JSON. So for a new tool chain, for a new compiler, new tool chain, this will boil down in implementing a pass that automatically generates this JSON file, like in Spatial. And obviously, the flags in this JSON file will be chosen with respect to the tool chain in hand. Okay, so perhaps we can see if there are questions now. Otherwise, we can take a little break and come back for the final part of this tutorial, where we'll have half an hour talk from mixed with a talk mixed with a demo by Artur. Are there questions at this point? Since there is one more question here, Reka.
Just a quick question: how much will the break take?
Only 5 minutes.
Okay, I'll see you in some 5 minutes. Never mind. Thank you.
Okay. And obviously, we will be here. So if there are questions during the break, please don't hesitate. Okay. So we will come back. Let's say 10:45. So in about 7 minutes.
Okay.
All right, so we're back on. Welcome back, everybody. So this is the last part of the tutorial. We will go through one last presentation by Artur. So here we are in this part here. We just went through the break, and we will work on design, space exploration, advanced topics with Artur right now. Artur will also complete this spatial demo that we skipped previously. Okay, so Artur, so please go ahead.
Okay, thank you. Okay, so just to complete the demo that Matt gave on spatial, I'd like to briefly touch what happened on HyperMapper sides of the communication with spatial in the example. And the key part that I want to emphasize here is that the spatial demo ran on a different mode of operation for HyperMapper, something we call the client-server mode. This is a feature of HyperMapper that allows a software, in this example spatial, to invoke HyperMapper to do optimization on demand. In this case, HyperMapper is acting like an optimization server and the software as a client, and that's why we call it the client-server mode. The idea here is that the software is able to launch HyperMapper as a separate process and have HyperMapper perform an optimization for the software as an internal step. So as Luigi presented in the introduction, here we had spatial use HyperMapper as a DSE, a design space exploration tool, in one of the steps of the compilation, one of the steps of spatial compiler. And the way that spatial does this is by simply triggering a flag in the JSON that triggers what we call this client-server mode. If we briefly go through the JSON for the gem that the Matt shown, we can see that you have this flag of the client-server mode set right here. A key difference that we have in this client-server mode that makes it interesting for this type of application, besides being able to use HyperMapper as an optimization server as an internal step, is that in this case, we are no longer giving HyperMapper a Python method to call and evaluate the function that we're optimizing. We no longer give it the black box function to optimize. Instead, what we have is that both processes, HyperMapper and in this case spatial, will run independently and in parallel, and they will communicate to coordinate the search. What does this mean? Spatial will invoke HyperMapper, will create a process for HyperMapper, and give it the JSON file that it automatically generated. As soon as it does that, HyperMapper will start the optimization process as usual by initializing the models with random sampling, but HyperMapper will choose what are the random samples that it wishes to evaluate, and then ask Spatial to evaluate these samples for him, for us, for HyperMapper. So here, HyperMapper will have to communicate with Spatial. We'll do an inter-process communication so that it can request samples to evaluate. Spatial can evaluate these samples and send back the performance metrics to HyperMapper, and then we can progress with the optimization. The advantage here is that, and I believe someone asked this briefly earlier, the advantage here is that this means that we can use HyperMapper with software that was written on other languages. This gives us a lot of flexibility in how we can use HyperMapper. We can use it as a step, as I mentioned, in the spatial compiler, which is written in Scala and not Python, like HyperMapper. We can use HyperMapper as a step of a process that's always running in background. You can use it in any form as long as you implement this communication and write this JSON file and feed that to HyperMapper. This means that we can easily integrate HyperMapper as a part of any tool or any existing framework. And the protocol that we follow and is implemented by HyperMapper, is a pretty simple CSV-like protocol, which you'll see that there's a great resemblance, a great similarity to the output that HyperMapper already provides. So let's do a quick illustrating example. Here we have our client, which is a software running, and we have HyperMapper acting as the server. We start this optimization by having the client invoke HyperMapper, create a HyperMapper process with a JSON file that it generated. And as usual, HyperMapper will start with the initialization, where it random samples a number of evaluations. Here, let's assume we're doing 3 initialization samples defined in the JSON. So HyperMapper will send a message back to the client with the parameters that are being optimized, which are defined in the JSON, and the samples, the values that it wishes to evaluate for these parameters. So here we have 3 examples. Once the client receives this, it will compute the value of the function for these 3 parameters, 3 parameter values, and send back to HyperMapper, reply to HyperMapper's message, again, with the parameters that are being optimized, the value of the function. In this case here, we will use the string that we defined in the JSON for the name of our objective. So in this case, we decided to call our objective value, and this is what we will use in the communication protocol. And then we'll reply in fashion parameter values and the value of the function at that point, parameter values and the values of the function, and so on. After initialization, this protocol continues during the Bayesian optimization in exactly the same way. HyperMapper will request a new parameter configuration to explore, parameter names, parameter values. The client computes the value and replies. And we follow these for as many iterations as we want, as we specify in the JSON optimization iterations field. And note here that HyperMapper always says how many iterations it's going to request, so the client knows how many function evaluations it will have to do. After we finish optimization, we run all of the iterations that we asked for in the JSON. HyperMapper will terminate as usual. It will write the results in an output CSV file that the client can then read and compute the optima or the Pareto front for the application and continue its execution. HyperMapper will terminate, and the client, for example, Spatial compiler, can go on with the compilation as usual. If you're interested in this tool, in this mode of operation for HyperMapper, you can find more information for it on the HyperMapper wiki. There's an entire page dedicated to this and a couple of examples provided in the repo that you can take a look that even implement this communication protocol if you want to use as a template. Before, I think this is a good point to have questions, if anyone has any, for the client server mode, if anyone is interested in this component of HyperMapper. Okay.
So I think this is maybe a good time to move into the advanced features of HyperMapper now.
Yeah.
Are there any? I think that I don't see any questions on this part here.
Okay.
Maybe we can wait a few more seconds to see if
yes,
there are questions.
Maybe on the Slack if anyone is typing.
Okay, please go ahead, Artur. Thanks.
Okay. So now I'll follow this presentation with, complement this presentation with some more advanced features of HyperMapper, which include some advanced topics in design space exploration. We have 3 topics that we want to cover in this advanced section. We will start with multi-objective optimization, which we have briefly touched when we saw the spatial use case. So, revisiting that use case, in some cases, we have multiple objectives that we want to optimize at the same time. For example, in spatial, we were optimizing runtime, and we were optimizing the resource usage of our FPGA. And the problem here is that these objectives, they are often conflicting. You often have that in order to improve, say, runtime, you have to use more resources, and Matt showed that in the plot DSE in the DSE Pareto file. And likewise, in order to optimize the resource usage, use less resources, we end up with a slower runtime. So we make the runtime worse. In this case, since we have this trade-off, we can no longer optimize our application and find the optimum point. Instead, what we look for here is what we have been calling the Pareto front. Very briefly put, the Pareto front is a set of solutions in our problem where we cannot improve one objective without making the other objective worse. So in practice, this Pareto front represents exactly this trade-off between both of our objectives. Here we have a quick example, an illustration of a Pareto front. We have two objectives. For simplicity, we'll call them objective 1 and 2 here. We have a set of green points that we are calling samples, which are the points that were explored during a design space exploration run, so during an optimization run. And we show with a blue line here the Pareto front. And you notice that the Pareto front contains all of the points where we cannot improve any objective anymore without making the other worse. So this Pareto front illustrates perfectly the trade-off that we have for this application. For example, if you look at the top part of the curve here, you have values that are very good for objective 2, but very bad for objective 1. And if you look at the opposite end, you see values that are very good for objective 1, but not very good or very bad for objective 2. And the idea here is that now we can look at this trade-off and select which point in this trade-off, which point in this front will give us a trade-off that we are comfortable with. So we can define, for example, a threshold in both of our objectives and say, I'm not interested in solutions that are above this threshold for objective 1, because then objective 1 is too bad for me. And I'm not interested in solutions that are to the right of this second threshold, because that means that the value for objective 2 is too bad for me. And then you can simply select one point in this region of interest that you say that you consider to have a good trade-off for your application. And this now becomes application specific. So you can select, for example, the trade-off that you want in runtime, how fast you want this application to run, but also resource usage, whether you want to give more resources for this application or save for another one in your FPGA. Before moving on to other advanced topics, let's have a quick look at how this works on HyperMapper. And here I invite you to open back the Jupyter notebook that we've been using for our earlier demo on HyperMapper. Here, this is the same demo Jupyter notebook. We're just continuing this.
Can you please, perhaps, Artur, for the people that perhaps joined a little bit more recently, just in case, can you please show them again how to reopen the demo Jupyter notebook 2020?
Yes, of course. So in this page here, we have the repo for HyperMapper. We have in the wiki installation instructions in case you haven't installed HyperMapper yet. You can come to the wiki, there's an install HyperMapper tab. And then there are instructions to install HyperMapper, whether you have Python already installed or not, all of the dependencies and how to set up. And if you come back to the HyperMapper repo, you can come to this example scenarios directory. In this demo directory inside, you'll find the Jupyter notebook that we're going to run for this tutorial. And in order to run this notebook, if you're not familiar, you just have to enter the HyperMapper repo. So here I have a terminal inside the root directory for HyperMapper, and you just run this Jupyter notebook command. If you do that, you'll get an output that's similar to this. You see here, I ran the Jupyter Notebook command. It will run some login and then print out this message where it gives you a link to access the notebook. Usually, when you run the Jupyter Notebook command, the notebook will open by default. It will open by itself. If it doesn't, you can just copy this link and paste it in your browser, and you'll reach this page where I'm at right now. You'll start here in the first example. In the first demo that we did, we covered the first 3 examples. If you are interested, you can run them. They should run pretty quickly and out of the box. So I invite you to do that if you're interested in HyperMapper. And from here on out, we'll continue from example 4. I'll give perhaps a couple of seconds in case someone is opening the Jupyter and getting through these steps to follow with us the tutorial. In the meantime, if anyone has any questions or comments, I'm free to take them. Let's give like 30 seconds, maybe a minute. I see some raised hands.
Sorry, could you kindly go back to the GitHub page where I can take a screenshot of? There you go. Can you stop there for a second?
Okay, so I also had a
Thank you. That's it.
I also had a general.
It's this page can be Reika. This page can be pretty easily found by searching HyperMapper GitHub, basically.
No, I understand. I just wanted the link of there's okay. So there's a link from HyperMapper to Jupyter, I suppose. It's a bit of there's for people who are actually familiar with the wiki page, it's a lot faster to know where Jupyter is, where this is, where that is. For us, it's going to be a bit of but I'm going to figure it out. Don't worry.
Okay, great. Thanks.
If you want, in our page for the DSE tutorial, we also have the link directly for the notebook there in the hands-on HyperMapper demo. If you click this link, you'll go directly to this page on HyperMapper repo showing the Jupyter. So let me show the link again, this one.
Okay, got it. Hands-on, got it. Yep.
Yeah.
Perfect.
Thanks, Reika.
Thank you.
I had a general HyperMapper question. I was just wondering why you grab initial values uniformly randomly, if I'm correct in assuming that, and if it's actually best to grab a set of initial values or to just run it from scratch. I mean, the first value will be random, I guess, but why do you grab a set of values first and not just run it immediately?
You need at least one value, but it's recommended to have more in order to initialize the models inside HyperMapper. Usually, if you initialize it with a single point, the model that you have in the early iterations is not very good. So it's useful and a good idea to start with a number of random samples that gives your model a general idea, very roughly, of the space of your application, so that then the model can take over and go directly to the points that are more promising. And answering the other part of the question, we do random sampling, but you could do some more structured approaches to select these points. If I'm saying that the model is not a good idea, it's not good to just use one sample from the space to initialize the model, you could use more structured approaches like latent hypercube. But in practice, we have found that random sampling usually leads to similar performance than, say, latent hypercube, and it's usually cheaper and simpler to use. So we use that as a default. We do have other options in HyperMapper as well.
Do you know why it's, doesn't the model update over time? So that, I was just wondering why a set of samples would be better than grabbing one sample and then iteratively updating the model as you get second and third samples, and so on.
Yes, the idea in general is that if you sample a single point, in some cases you might end up, for example, if we sample a single point here, in this example, in this 1D branding example, you might end up giving the model a bad impression of the space. If you sample a single point, the model will think that the space is a straight line because it knows nothing else. But if you sample too few points, you might end up giving the wrong impression to the model of the space. And it would, for example, focus too much on a local minima before starting to explore. Giving a good amount.
The short answer to that question, Hampus, is that you can even start with just one sample at the very beginning in the initialization phase, and you will eventually get to the optimum. It's just a matter of how fast you get there.
Yes.
Okay, so for me that sounds like it's not prioritizing exploring as much as you would like early if you have few samples. Would that be a correct assessment?
That sounds like a good remark. Yes.
Yes,
okay.
A good summary. Yes.
Then I know. Thank you.
Thank you for the question. Okay, so if we don't have other questions, let's move on with the examples for now. Going back to the Jupyter, we will follow from example 4. And here we'll show an example of a synthetic function with multiple input dimensions and multiple output dimensions, multiple objectives. Here we're using another synthetic function from the Bayesian optimization literature. It's called the DTLZ function, and it is specifically designed to test Bayesian optimization or other optimization solutions for multiple objectives, so optimizers for multiple objectives. In this function, we have 6 real input parameters defined in the interval between 0 and 1, and we have 2 objectives that we are interested in optimizing. In this cell here, you'll see that we define this DTLZ function. We can run it to define our method. It's, again, we're running HyperMapper on the default mode, so we define a Python method to run our application. It will receive as input a dictionary containing all of the input parameters as keys. Here we simply number them from x1 to x6. We then compute some constants and our objectives. And here you will notice in these 2 lines that we are computing 2 objectives that we chose to call F1 value and F2 value. Here, when we return these values for HyperMapper, since we have 2 objectives, we can no longer return a single number to HyperMapper. So here we will use a different interface and return a dictionary instead. Just like we receive a dictionary with the inputs as keys, we will return a dictionary with the outputs as keys to HyperMapper. HyperMapper will understand this interface seamlessly out of the box. You don't have to change anything other than returning the dictionary instead of the number. HyperMapper, in practice, always accepts both returns, either a number if you have a single objective or a dictionary if you have multiple objectives. Next, we define our JSON file. We will use Python again to define this JSON, and we can, again, read it back to see how it looks like. It seems that it's taken a little while to run. Let me show the file here while it runs. Oh, it didn't generate the file yet. It seems like the Jupyter got stuck. Let me rerun it so that we can have this file. I apologize for the technical issues. Looks like my Jupyter notebook stopped running. Let me restart it. So I'll rerun a couple of cells that we used to build HyperMapper early on, which should be fairly quick, and then return to the fourth example. Please just give you a few seconds to finish running. Okay, so coming back, apologize again for the interruption. We define our DTLZ function, and then we write the JSON file and read it back to check if it's the fields that we defined. So here we gave a name to our application. We call it the DTLZ1. We give names for both of our objectives, and here it's important to use the same names that we're going to use in our Python method. So here we are returning f1 value and f2 value, and we have to tell HyperMapper that this is what we're calling our objectives. So we'll call them here f1 value and f2 value as well. We'll use a Gaussian process model again, run for 10 optimization iterations. We do not specify the initialization samples, so we'll do 10 by default. And we have 6 real input parameters going from x1 to x6, all defined between 0 and 1. We can then run HyperMapper in this example by calling the JSON file that we generated on the fly and giving it the DTLZ1 function that we just defined. And here, I invite you to run this cell, and we can look at the output. Once again, you see that HyperMapper will print out how many samples it did for the initialization, the headers for the input parameters for both objectives and the timestamp. And then here we have the values for all parameters and the objectives, and both objectives and the timestamp, all 10 random samples that HyperMapper did. And following this trend, HyperMapper will then print the same thing for each optimization iteration, all input parameters, both objectives that we're optimizing, and our timestamp. After HyperMapper finishes, it will run for 10 iterations as we requested. It will save the output to the CSV file, just like we saw on previous examples and on the spatial use case. And then we can use 2 HyperMapper scripts to compute and plot the Pareto front for this application. These will be the same scripts that we saw in the spatial use case. We'll call the compute Pareto script, which will compute the Pareto for our application. We give it as a parameter, as an argument, the JSON file that we defined. And then we'll call a plot DSE script, which will receive as input a Pareto, the JSON file. And we'll also give it an output file where we want it to save the output image in this case. Note that both scripts will plot some login information on the screen. They will both print some login information. The Pareto, both scripts will print out what's the name of the output file, and both will print out the number of points in the Pareto front. You can see the same output here, the outputs in PDF. and the file of the Pareto front that it found. And here we can quickly visualize this image on the Jupyter notebook. Here, this is the Pareto front that we found for our DTLZ application. Now, moving on back to our presentation, we'll cover a second advanced feature of HyperMapper, which we call, and it's usually called in the Bayesian optimization literature as constrained optimization or constrained Bayesian optimization. And remember that here in the spatial use case that we saw earlier, and I believe Luigi mentioned as well in this introduction, we have some feasibility constraints, as we call them in the search space. We have some parameter combinations that lead to designs that are impossible to synthesize. So for example, if we increase the parameters of parallelization and memory buffering too much, we will end up with a design that requires more resources, more logic units, or more memory than what the FPGA provides. And this is obviously not a valid solution for us. This is not an interesting solution for us because we cannot use it in practice. So we say that these solutions are infeasible. And when optimizing an application with constraints in the search space, we are then looking for the best feasible solution in HyperMapper. And this is done naturally by HyperMapper if you trigger a flag again in the JSON, telling it to use feasible outputs. The flag is basically called feasible output, and you give it an enable feasible predictor flag set to true. This is all you have to do to set HyperMapper to run with feasibility constraints. The reason we do this, to show you why we do this, we have here a quick illustration of HyperMapper running on the GDA spatial benchmark. Here we are optimizing for two objectives, cycles or runtime and logic utilization. And here we show two variations of HyperMapper. One without the feasibility model that predicts, that shows us where the feasible points, that tries to find feasible points. And here we show the points that were explored and are feasible in blue, the points that were explored and are not feasible in red, and the Pareto front that the optimization found in this blue line. Similarly, we show another optimization of HyperMapper, this time with the feasibility predictor on, with this model that predicts feasible points turned on. And here we show again the feasible points that it found in black and the infeasible points that it found in green. And once again, we show the Pareto front that it found with this black line. Note that when we have the feasibility predictor on, we find a much better Pareto front with many more samples and points that are usually much better than the version without the feasibility model. For example, here we have a point with that's twice as fast in runtime with only 10% more logic utilization. And the reason for this improved performance of HyperMapper is that if we do not use the feasibility model, we end up wasting several function evaluations, several iterations of our Bayesian optimization with samples that are infeasible. Notice that without the feasibility model, HyperMapper wastes a lot of samples in this region here where all points are infeasible. Let's quickly go back to the demo now for a minute and see how to trigger this, how to use this in practice. So here I'm back to our Jupyter Notebook demo. We will follow up with example 5, and this is our last example, where here we're optimizing another synthetic function from the literature, this time a function that's called the Chacon-Hames function, which is designed to evaluate and to validate optimization methods with constraints. Here we have two real input parameters defined between -20 and 20. We have two objectives that we're trying to optimize. And we also have two constraints on the possible values of our parameters, x1 and x2. We have two inequalities here that we want to have satisfied for a configuration, for a parameter combination to be considered valid or feasible. We will define this function once again, a Python method for HyperMapper, dictionaries as input. And here we'll compute both objectives, F1 and F2. And we will also compute our constraints. We will check if these inequalities that we define are satisfied and store this on a Boolean flag that is true if the point is feasible and false if the point is not feasible. When returning this to HyperMapper, we will once again return a dictionary with both objectives and this time also a feasibility flag valid that tells HyperMapper whether this point is feasible or not. And this information HyperMapper is going to use internally to guide the search towards feasible points. We've also defined a JSON file for our application. We can read this file here, and most of the fields we are familiar with by now. We have an application name, optimization objectives, initialization phase, and here we have a new field, as I showed. We have a feasible output field in our JSON file with the enable feasible predictor flag set to true. This is all we have to do in order to tell HyperMapper to turn on the feasibility model and consider that this application has feasibility constraints. Besides that, we also define, again, both our input parameters, real numbers between -20 and 20. With these two components, we can then run HyperMapper. And this time, we gave HyperMapper 20 initialization samples to make sure that HyperMapper finds at least one or two feasible points during the initialization phase, because for this benchmark, the feasible region is quite relatively small. Here you'll see that during the random samplings, most of the points that we found are infeasible, which are also useful for HyperMapper to understand the objectives better and how they behave. But a few points are feasible, and they are very important for HyperMapper to start to understand where can it find the feasible points in space. If you later look at the optimization iterations that HyperMapper is performing, you'll see that it's now outputting a valid flag that tells if the point that HyperMapper chose to explore is feasible or not. And you'll see that most points that HyperMapper is exploring are feasible. So HyperMapper is really trying to optimize these two objectives, find the Pareto front for these two objectives, focusing only on the feasible region of the space. You notice this, the majority of points, it should be the same if you run it locally on your machine. The majority of points will be feasible. In a sec, we asked HyperMapper to perform 20 optimization iterations here. So we leave it running for a little second. And once HyperMapper finishes, it will save the output on a CSV file. And we can then read this output back, compute the Pareto front, and plot the Pareto front that HyperMapper found for this objective. This is the Pareto front that we found after 20 optimization iterations. And just a note, when computing the Pareto and plotting the Pareto, HyperMapper will only consider points that are feasible. It will plot the Pareto front for feasible points only, because those are the only solutions that we are interested in these applications, in applications with feasibility constraints. Now, moving ahead, we have one last advanced feature of HyperMapper that we wanted to introduce, which is what we call prior injection. And this is actually a new development of HyperMapper that we've been working with in the past month. Our idea here, and Luigi has mentioned this briefly in the introduction, is that when we are optimizing these applications, the user behind the application and behind HyperMapper usually has an idea or an intuition or some values for some regions of the space, some values for the parameters that the user can expect that will be good. For example, if we're optimizing an application, we want to decide how many threads we use on a CPU with 4 cores, as Luigi mentioned. We expect that this prior would be maybe a Gaussian centered around 4 or around 6, meaning that values around 4 or around 6 are good, maybe a bit more, maybe a bit less, but we expect values that are too far from that to be bad. This is simply illustrated in this little figure here on the right, where we see 2 input parameters, x1 and x2, and they're basically trying to tell the optimizer that we expect good solutions to be on the right side of x1 and the bottom side of x2. So we want to focus on this region right here. Our idea with this is to help guide our optimization with HyperMapper towards good solutions with good regions with good solutions. We want to encourage our optimizer, in this case HyperMapper, to at least focus first on this region where we think it will find the good solutions we are looking for. And the way we do that is a little bit technical, but keeping it simple for now, is that we combine these priors in HyperMapper with the Bayesian optimization model that we already have inside, the model that will observe the data, learn, and move towards the optimum. And our goal with this combination is to have the priors help HyperMapper eventually find this optimum faster. So we give the initial idea and the model will refine this prior until it finds the optimum, but also allow HyperMapper's model to overcome the prior and guide optimization, learn from the data, and guide optimization away from the prior to a new optimum region if for some reason the user is wrong, or if the application behaves a little different than what the user expected. This has been in development in the past few months, and we already have some results with this feature added in. Here, I'll show some quick comparisons of HyperMapper with the prior and HyperMapper without the prior on 3 spatial benchmarks. And you can see from these blue and red lines that the prior usually helps HyperMapper have better performance. So here, for example, in the shallow CNN benchmark and the deep CNN benchmarks of spatial, we see that HyperMapper with the prior converges faster than HyperMapper without the prior, even though they find the optimum, both find the optimum eventually. And similarly, we show the same comparison on an MD grid benchmark of spatial. And here we see that the prior actually helps HyperMapper finds better solutions. It finds a solution that is approximately 1.3 times faster than HyperMapper without the prior, showing that there's great benefit to HyperMapper if we can set this prior properly and have this prior help HyperMapper in optimization. Let HyperMapper leverage this prior during optimization. As I mentioned, this part is not in the public repo yet. This is under review in a machine learning conference. The details of our implementation are a little bit technical, but if you're interested, we will release the open source version of this in HyperMapper and an archive version of this paper while it is under review in archive in we will release both these things in approximately 2 weeks. So look forward to it. At last, I'll conclude showing then what is the full HyperMapper framework that we have right now. So HyperMapper will have an input, a search space declaration, and HyperMapper will do an initialization phase, usually random sampling, as we have been doing. HyperMapper will then fit its models, its machine learning models that helps it predict the space. We predict the space, the values for the objectives and the feasibility constraints, predict if the points are feasible or not. Based on this information, HyperMapper will try to predict which points will be Pareto or optimum if we have only one objective. We can use the black box function, either run it by default on HyperMapper or use the communication in client server mode to evaluate these points, which will give us new data to learn from. And we can refit our models and continue Bayesian optimization for as many iterations as we want. And after we are satisfied, after we fill all of our iterations, we can then output the Pareto front that we found and analyze our results, analyze our optima points. This, I'll stop at this slide here, highlighting our HyperMapper framework. These are the advanced features that we wanted to share with you. And now I think I'll hand the word back to Luigi, and I think we'll follow up with some panel and discussions, maybe some questions.
Thank you very much, Artur. This part has raised a bunch of questions and tried to answer them in real time on the chat. But I think this question by Augustine can actually be taken verbally if you wish. I can maybe read it myself, or Augustine, if you prefer to ask it yourself, raise your hand, okay? So the question is, I guess the performance in this case depends highly on what priors you feed, right? What did you use for the experiments? Because if priors are too good, it's almost like knowing the solution beforehand. So this is a very good question. Can you tackle this question, Artur?
Yes, this is a very good question. And yes, it depends highly on the priors. As I mentioned briefly, the idea is that the priors will help us converge, and we converge even if the priors are wrong. And the point that I want to make it is that, yes, if you give extremely good priors, say you give a prior that's almost 100% picked at the optimum, then optimization is going to be very fast. You're going to find the optimum very quickly. And on the other side of the spectrum, if you give a prior that is very bad and extremely wrong, then you actually end up slowing down convergence. HyperMapper will still find the optimum, but it will make finding the solution much slower than not having the prior. Answering your question more specifically, which kind of priors we gave in these three benchmarks here? We have here on this black line an expert configuration that was provided by Matt. The same Matt also provided us with the priors for these three benchmarks. And I have an example here that I can show you. It's a little bit extensive. The full list of priors and parameters that we optimize will be on an archive version if you're interested. But basically, we asked Matt to give us a probability distribution of each point, since we have ordinal values, of each value for each parameter being good. And you see that here Matt gave us this probability, and it's not 100% peaked. You see that in most cases, the probabilities are quite low, below 0.5. But this is the intuition that Matt gave us and gave HyperMapper in order to help find us this optimal region, this better performance. Have I answered your question, Augustine? Would you like to make a follow-up?
Yeah, that's really nice. Thanks. So in a sense, his expertise was better for, his expertise made better performance as priors for HyperMapper rather than just giving the answer, right? The expert configuration.
Yes, the idea is that you have Matt knows how this space will perform, and he has an idea of what values will be good, but finding the exact points that are really good and feasible in this case can be a little tricky. So if you combine his idea with the model learning, the machine learning of Bayesian optimization, we can kind of reach the best of both worlds, combine the best of both worlds to find these better values.
Yeah, to just
yes,
just
exactly.
feed the intuitions, right? But
exactly.
not the exact values, because we don't have the exact values, but an expert would have an intuition of where they would be.
Exactly.
Really nice. Thank you.
Exactly. Thank you for the question. Very
right.
interesting.
Right, and the point is that often we don't have experts, right? And in that case, you just use the plain version.
Yes.
But there are cases, if you think, for example, the way Intel create generations and generations of their hardware, when they create generation T+1, they have all the information from generation T, and probably it's an incremental work. They don't redesign the chip from scratch. So they can probably use all that knowledge from generation T and inject the knowledge to iteration at T+1. And so that knowledge will not be the optimum, of course, but it can give a little boost in the performance of the optimizer by accelerating the optimization and getting better performance.
That's an excellent example. Exactly.
Yes, I think there is another question here.
Yeah.
Joel?
Hi, yeah, can you hear me?
Yes.
Good. So my question is if HyperMapper really needs the evaluation of the value that it wants to optimize, although it already knows that the configuration of the parameters is not valid.
It's good for HyperMapper to have this information, even if the parameter, the configuration is not valid, because even if it's not valid, it helps HyperMapper better fit the model. The more data we have, the better our internal model in terms of predicting the objectives. So it's useful for HyperMapper to know this. It helps accelerate convergence.
Okay, interesting. And on top of that, is it possible to combine the values? So if I say I have two variables, x1 and x2, ranging from 0 to 10, but I know that the sum must be below 10. Or would I do that by having these constraints and just saying, okay, this one was not valid?
Yes, I'm understanding that you have two parameters, let's say x1 and x2, and you want to optimize them, but they have to be both less than 10, right?
No, the sum of both.
Yeah, sorry. Yes, I'm sorry. I misspoke. The sum of them has to be less than 10, and they can be higher. Yes, you combine the defining if a point is feasible or not is entirely on the function side. So you can do that. For example, here in our check on Huygens example, we have a similar case where we want the sum of the square of both of our parameters to be less than 225. So you would do the same thing a little bit on the fly here. You define this flag as being x1 plus x2 less than 10. And then you just tell HyperMapper whether this was true or not. HyperMapper does not know that this is the constraint. It has no idea what the constraint is. It tries to predict it.
And it will not choose its parameter for the next iteration based on that constraint.
Exactly. As HyperMapper sees feasible and unfeasible points, it starts to learn that, oh, okay, x1 and x2 cannot be both high because that's going to be unfeasible. So I'll predict a little bit lower.
Yeah.
Exactly.
Okay, good. Thank you.
Thank you.
Okay, so perhaps we can now move into the final session. This will be just a few minutes to wrap up. We went through a bunch of different topics around optimizing high-level design space exploration features and their implementation in HyperMapper. And we've seen a very concrete use case, which is the spatial programming language and compiler. So at this point, I would like to open maybe for general questions on the tutorial or some higher level questions and whatever topic the audience will think interesting here. So Artur and Matt and myself will be here to answer these questions. We'll also stick around a little bit longer after this short panel session to answer questions that are more like practical in terms of installing the software and making it work. As you've seen, installing HyperMapper was very, very simple. There were only a few lines and it runs in Python. So Python, it's a language that runs pretty much on all sorts of platforms. also the special install was also pretty simple in a few lines. So, but if you have problems with those, we will stick around after this panel session. So feel free to ping us on Slack so that we can address these questions afterwards. Okay, so let's open this short panel session, and I would like to maybe start asking if there are questions in the audience.
Just to maybe emphasize here, I mean, we welcome many questions that we have. The more questions, the better.
Yeah, so like questions, for example, also, do you think this is something that can be applied to your own tool chain? What are the limitations that you see? Is there anything that you think is missing from these 4 high-level features that I introduced, which is the type of variables, categorical, ordinals, real variables, the multi-objective optimization feature, the prior injection, and the feasibility constraint feature? So I think we built this whole framework around these 4 features, but maybe we missed some other features that are also interesting for computer systems optimization in general. So we are very keen to hear from you if there is anything that you think is missing here, and if this can be directly plugged in your own tool chain. Any comments?
And we have a first question from Joel.
Yeah, so in my use case, I need to sort something, or more specifically, I have a topological sort of something, and I wonder if one topological sort is better than some other.
In this
Right.
case,
And this is, sorry?
Go ahead.
Go on.
Yeah, and this is currently not, I don't think, easily applicable to your like search space. But yeah, I wonder if I could just adapt that somehow, but I have no idea currently.
So can you topological sort? So what do you mean by that more precisely?
Yeah, if you have a graph and a dependency graph of a directed acyclic graph, then you can sort them in some way, or if you imagine some instructions that need to be in some order. And I wonder if one order is better than another.
Right.
And in this case, how would you define if one order is better or not? Do you consider the path, the connectivity? Do you have a metric for that?
I use that order and compile that down to some assembly, then run the code and see how fast was I.
I see.
I think the way to encode this in HyperMapper is to go through some graph embeddings first, which is a little bit like a technical detail. But so if you go through some graph embeddings first, that means you basically transform your topological configuration into something that is then searchable. And then you can define an objective function that ranks all these different configurations, right? And so at that point, you basically are able to encode that in HyperMapper. The only thing that you need is to have the graph embeddings first at the beginning of the pipeline, and then you can just apply HyperMapper as it is. That's a very interesting question. I actually, if you end up doing that, please keep us in the loop, because I'm very curious to see how does that look like in practice. So that sounds like an interesting project.
Okay, is that graph embedding already part of HyperMapper?
Oh, it isn't. This is the first time I get a question like this. So I feel like if there is interest in the community, I see that it's not like a very isolated case. That may be something we can add at some point. Graph embeddings are pretty popular in the machine learning community, and what they do is to take a graph and transform it in basically a string.
Yes, and I can then use like what is it called?
So I guess depending on how you do the graph embedding, you can transform the output as a categorical variable or an ordinal variable also. So if you can, in some sense, order them, may be difficult with graphs, but if you can order them, then ordinal variables will be better to be used. But otherwise, it's just a categorical variable. And then on top of that, you can also consider, if that's one categorical variable, if you have other things that are also part of your search space, you can just add them on top of that. So you will have a search space that is not just the categorical variable, but also other things if you have them.
Yes. Okay. Thank you very much.
Yeah. So keep us in the loop if you end up implementing something like this, and potentially consider also in contributing back to the open source code if you implement the graph embedding that in HyperMapper. Then in that case, we're very happy to pull a request for that. Then.
Yes, I will. Thank you.
Thanks for the question.
Thank you. For these, before moving on to the next question, if you have it, for these applications, we are very interested in knowing what are you doing with HyperMapper and how are you using it. So if you plan on using HyperMapper to your application, we invite you to join our Slack channel or to keep in touch with us so that we can maybe provide some support and see how things are going. This is very exciting for us. We have any other questions?
Any other questions here?
I think Sriram maybe demonstrated interest. I'm not sure. If anyone has interest, please raise their hands.
So perhaps one of the questions that has been asked on a separate channel today that I feel it's pretty interesting is Matt. Matt, are you here?
Yeah, I'm here. There might be a little crosstalk though, because we're in a studio apartment with 2 meetings going on.
No problem. So perhaps one of the questions that was asked in a different channel on Slack about this tutorial is the following. Perhaps you can try to answer that question because you had like this very hand-on, pretty long experience on doing DSE in spatial. So the question was that we have seen in other fields, and I'm doing my version of the question because I don't have the question right now in front of me. So I'm doing the question of like I'm doing a revised version of the question, try to stick with the idea of the original question. So we've seen in other fields, we've seen that users actively learn from these optimizers, right? So here in HyperMapper, we have a machine learning tool that is running behind the hoods and behind the scenes. And basically this machine learning tool will eventually have some knowledge. And we wonder if that knowledge can be used by the user. So one of these examples, one of this very compelling example was, which is perhaps the most famous example, is the Lee Sedol, the world champion in the game of Go. Lee Sedol, after playing and actually losing against AlphaGo a couple of years back, he declared that he learned some new strategies, some new Go strategies that he didn't think of before. So this is the world champion of the game of Go that is saying basically that he learned something by playing against an artificial intelligence that was basically a machine learning tool to play the game of Go automatically. And so I wonder if something like this, where the user, which is this expert, maybe user that has been doing the optimization by hand for many months, maybe before turning into something that is automated. Do you think that something like this also happens in the case of HyperMapper? What's your experience with the spatial optimization? Did you learn anything yourself when you run HyperMapper on spatial?
Yeah. Can you hear me okay?
Yes.
Okay. Yes, I think the short answer is yes, you do learn something. Well, I learned things by using HyperMapper and automated DSE that I wouldn't have learned otherwise. And so I wouldn't say it's as large scale as what you just described with Go. But the thing I would point out is that a compiler and an automated tool like this has a much broader view of the application that a human would not be able to view. So maybe GEM isn't the best example for this, but there are more complicated applications with more complicated loop nest structures. And in these, it does become really tricky to understand the relationships between your parameters. And so what happens is, like as a designer, I would think the hotspot in the application might be in one part. And the DSE tool, since it had a much broader view and could automatically search the space, is going to tell me that actually the hotspot is somewhere else. And so I think this does happen pretty much every time you use an automated DSE tool or HyperMapper specifically. I do learn a lot about my own application that I didn't realize was a hotspot before.
Right. This is interesting. So the optimizer isn't, but also perhaps to feedback to feedback on the knowledge that you learn that the optimizer gathers over the exploration versus exploitation trade-off, and basically learn a little bit about how to do that better as a manual optimizer, basically, and seeing a little bit better what the bottlenecks are and so on.
Yeah, there's a lot of value in
Good.
having a broader view of the application that only a machine can have.
Right. Good. This is interesting. So perhaps another question that I would like to ask to Artur. So Artur, what are the lessons learned by actively looking in implementing HyperMapper for a couple of years now? So how difficult it is to deploy HyperMapper in a new programming language compiler toolchain, for example, maybe in a new hardware design application or things like that? What do you think?
This is an interesting question because there's a tie-in between both points. Implementing HyperMapper, one thing that I didn't expect it would be a component. All the exciting research part aside, there's so much to learn there. But implementing HyperMapper and making it work is one thing, but making sure that the tool is good to use, flexible, and generic, you will recall it took a great effort from us. Make sure that we try to cover, we specify these 4 features that we want to have on HyperMapper, and we try to build our tool around it because we envision that people need these features. They need the different types of parameters. They need constraint optimization. They want to optimize for multiple things at the same time, and they want to inject their priors into optimization. People want to do that, and doing that in a way that it's easy to use, flexible, and that's not like a headache to make a new feature work it was interesting to tackle, and we had a lot of discussions on this. And then at this point, I think we have a pretty flexible tool. I think right now it will be pretty easy for people to get our tool and apply it to a new compiler, a new tool chain. And I think the key here is that as soon as the user understands what we need to specify, so in our case, the JSON file is the critical part, and how to evaluate the methods. For example, in this case, if we're applying to a new tool chain, it would be learning the communication protocol between HyperMapper and the tool chain. This becomes extremely straightforward. So for example, for the communication protocol, we provide a little template on the GitHub. It's pretty simple protocol. If you can get this protocol running and then suddenly you want to add another objective to your problem, for HyperMapper, all you have to do is add a second objective in the list of optimization objectives, nothing else. If you want to add a constraint optimization, you just add a field to the JSON saying, enable the feasible predictor. So on the HyperMapper side of things, we try to make the interface very simple to expand and to add these new features and play with them. So I hope it's easy to use, and I think we are at the point that if you learn the basics, you learn the masters pretty quickly. So I think it's pretty easy to integrate. So if people are interested in using for new applications, I think they won't have much trouble with it if they follow this tutorial.
Great. Thanks for your answer. Is there any other question that the audience wants to ask? Anything comes to mind?
Has someone raised their hands? David?
Oh, David. Okay.
Yeah, I might have missed this, but how well does it work for if I know incorporating relationships between the dimensions? Like I know I only want categorical value 1 if 2 or something like a certain value for categorical dimension x if y or something similar to that.
Sorry, can you repeat the question? I didn't quite hear it.
I might have missed this in the presentation, but I was just, it seemed like you were solving for the optimal for each dimension. But like as the user, if I know
for the optimal what?
If I know that a valid solution, that a certain that dimension x can only have certain values if conditional constraints between dimensions. You know, if you pick a value for x, then that means y can't be in some range. Is there some way for me to encode that? It was like as a into the system. It seemed like there was just a way to encode the ranges of values.
Right. This is this is an excellent question. So you're talking about conditional type of variables. So where you basically define a variable and then the values of another variable or parameter will depend on how you define the first parameter. Is this correct?
Yes.
Yeah. So for example, if you think, for example, the example I had comes to my mind real quick is so if you decide to merge two loops, then maybe the unrolling, I don't know. A simple example is on neural networks, for example. So if you have a number of layers, then the number of nodes inside the layer will be conditional to how many layers do you have, for example, things like that. So we are aware of this, and I think we will need to develop this conditional variable space, search space, for when we will work on plasticine, which is the next step for HyperMapper. And for now, you can find some workarounds, but they're not like the optimal way of doing this. And to be honest, I don't think there is a very clear research answer on how to do that in a very efficient way. So right now you can wrap up your conditional space in a non-conditional space in some way, and then you run the usual HyperMapper. But I think there can be things that can be done better, and it's not entirely clear what's the answer for that, like from a research perspective. But we are planning to work on that as a next step. That would be another of the features that may be added to HyperMapper sometime in the next few months. But we don't have that, and we don't even have a clear solution on how to do that in an efficient way right now.
Okay. Well, thank you very much.
You're welcome.
Thank you. We have a question from Sriram, and I will read it out loud. I will search for HyperMapper, and excuse me if I sound naive. Is there any package similar in RStudio like HyperMapper? And unfortunately, no. I mean, there are packages. I imagine that there are packages in RStudio for optimization like HyperMapper, but HyperMapper is not in RStudio. HyperMapper is implemented in Python only. So HyperMapper is not in RStudio, and I don't think you could use it out of the box. But it would be possible, perhaps, to make both things, use HyperMapper with your current application in RStudio with our communication protocol, our client-server mode.
Does it answer the question, Sriram? Maybe you can ask a verbal question at this point. Oh, yes, okay, so it does.
Ah, good.
There is another question that perhaps I got on a private chat, sorry. So I will just maybe mention it here. So what is the current encoding language for the prior? I think you briefly mentioned that in your presentation, Artur. Can you please show again what the prior looks like? Maybe you can share your screen and.
Yes, let me share my screen and then give 2 quick examples here and then provide an answer. So can you see my screen now?
Yes.
Yes, perfect. So let me use this image here as an example. Answering your question first, in general, we define the prior as a probability distribution. So all the user provides is a probability distribution on what points are going to be good. So here, for example, we provide a sort of a bell-shaped probability distribution, saying that we are more likely to find good points in this rightmost region. And this probability distribution, as we show here, can take any form really. Here we show examples with a beta, where we have bell-shaped distributions, exponential distributions, decay distributions, or uniform distributions. So any form of closed form distribution is accepted by HyperMapper. Also, we have an example. I showed you briefly an example of the priors that we used for a spatial benchmark. And here, instead of a distribution, a closed form distribution, we have a list of probabilities. So we basically have the probability of each value being good in an ordinal, or at the bottom, a categorical parameter. In short, the answer that I give is that any type of probability distribution, any form of injecting this probability distribution is accepted in our approach. So closed form, list of values, a hand-drawn prior if you want, anything that we can encode as a probability distribution is usable with our solution. Perhaps a quick addendum. We have also experimented with other types of priors, Gaussian centered at specific points in the space, and even synthetic priors built with kernel density estimation. So we have a pretty flexible interface for defining these priors.
Okay,
I hope I answered the question.
Yeah. So there's a question, follow-up question on this is why we didn't use probabilistic programming for the prior. And perhaps I can take this question. So I think definitely probabilistic programming is a way to tackle this the implementation of the prior in HyperMapper. Definitely, probabilistic programming can generally be used to implement parts of this toolchain. And there are some examples of Bayesian optimization tools out there that actually use probabilistic programming. One of the examples is the recent Facebook tool, which is called BowTorch, I think. That is based on probabilistic programming. So the probabilistic programming in this context of the prior will not really change very much the algorithm itself. It will probably help on how to code this thing in practice. But the algorithm itself that is behind the prior work that we did, it's actually a recent work that will be released on Archive in a couple of weeks and has been recently submitted to a top tier machine learning conference. It's based on a new algorithm that it's a new algorithm that cannot be just implemented by calling some probabilistic programming function. It's a combination of prior and data model that models the new data, and basically how to combine this information in a Bayesian meaningful way. So I'm being a bit vague here, but the answer may be a bit long to describe how that works in very, very specifically in practice. So, but yes, so the answer is definitely yes. I think we can use probabilistic programming to implement even the whole HyperMapper framework. a few years ago when we started, we didn't have that approach. I know that probabilistic programming is becoming more and more popular in recent times, and I agree that HyperMapper can be re-implemented using that language, those languages. But that doesn't really solve the prior optimization type of stuff. So that the prior, it's a completely new algorithm. It's something that we introduced for the first time, not only in the computer systems community, but also in the broader machine learning and optimization community. So this is a contribution from our research work. I hope this answered the question. Any other questions before we wrap up? Okay, so in this case, thank you very much, Artur. Thank you very much, Matt, for, oh, there's one more question by
Reika.
Yes, this is also a naive question. Sorry, I'm a first-year PhD student, very much into functional programming. How would you see me as a naive researcher implementing what you have done into something like, oh, Scala is pretty much functional, but maybe OCaml or such?
So re-implementing HyperMapper in a functional programming, in a functional programming language.
Yeah.
Okay.
Maybe if it's like completely out of nowhere and
what kind of advantage would you see in this context of the? I'm sure there are plenty of advantages, but can you cite maybe a few?
Absolutely.
In the specific context of the HyperMapper.
Just the fact that we PL community love ML and functional programming is just something that we prefer. So we just want to wake up and see trees everywhere. So that's pretty much why. But that's what I think. But I don't.
I would love to keep talking about this question. I
could email you.
Really have a, yeah, definitely. I don't really have an answer right now. How difficult it is? It will be probably a little bit challenging because there is a lot of like math and algorithms that have to be, I guess, at least
included in terms of libraries, perhaps.
We do use libraries, but a lot is implemented in HyperMapper. So most of the algorithms are actually implemented by us in Python. We use a little bit of scikit-learn. We use a Gaussian process library. We use maybe another library for visualization purposes.
A lot of NumPy to handle numerical values as well.
Yeah. I think it's definitely possible. It's probably not something that you do over a weekend. It probably will take, I will guess, a few months to be honest, because this is numerical methods and probabilistic models and so on, and those are notoriously difficult to debug. So translating it from Python to a functional programming language may be a bit tricky, just because you have to make sure that everything is implemented properly. And but that's an interesting question, and I'm happy to discuss more about this offline, and we will be supporting you in case you decide to do that.
Thank you.
Thank you.
Okay, so if there are no questions left, we'll just try to wrap up. So this was very interesting for us to receive all these questions, and I hope that this tutorial will not end up here, and we will get more questions afterwards. So feel free to drop us a line on emails or later on, or on Slack during the PLDI conference. Thank you very much, Artur. Thank you very much, Matt. And thank
Thank
you
you.
all for joining
joining.
this event. Okay, enjoy your PLDI experience.